I'll start from the logic because logic is very helpful. Logic will help you to build, or it will try to understand what are the things that will be there. So let's start from that logic. See, if I'll try to create the topics of logic, either you can call this as the logic or you can also call it as a mathematical logic. If I try to say that, so the mathematical logic is basically divided into 5 to 6 topics. The first one, which is called as a propositional logic, and second topic that we are having is called as a logical equivalence, and third topic we are having, which is called as the inference rule. And now we are having, which is called as a quantifier, and then we are having, which is called as a nested quantifier, and then quantifier with inference rule. Quantifier with inference rule. This whole topic has been divided into, the logic has been divided into 6 topics. Now if I will try to say that, it has been divided into 2 models. The logic, the first model is basically called as the basics of logic, and second model is the advanced logic. So this is basically basic. It will help you to understand, to create the basics of the whole subject. And once we are comfortable with that, and out of that, the most important one is logical, sorry, which is nothing but the inference rule. Because propositional logic you may have studied somewhere, logical equivalence you may have also studied somewhere, maybe in 11th or 12th you may have studied logical equivalence, but the inference rule you may have not studied anywhere. So understanding the inference rule is very, very important. And now we are having this quantifier, nested quantifier, and then quantifier with inference rule. So this is very, very important related to that. So basically the whole logic, as I told you, basically it will be divided into 2 models. The first model is basically the basics of logic, and second model is advanced model, which is a quantifier, the nested quantifier, and then quantifier with inference. This is basically the advanced model. Let's go and let's try to start why we requires the logic and what is the main important topic related to that. See, many times when we are studying about the logic, so here I'm starting, please everyone pay attention. See, whenever we are starting the logic, many times the students thinks that, what is necessary to go and to understand about the logic, because gate is this examination, gate is very tough examination, and why they will require the concept of a logic. Let me tell you. See, the logic will always help you to understand the validity of a statement. Logic will always help you to find out the validity of a statement. So for example, suppose if you people have done, or if you have clear gate examination and you are going for MTech or you are going for MS program, then at there you may write your research paper. So when you are writing your research paper, you have to write the whole paper. So in that paper you will try to use the English statement. So suppose if you have written any type of statements, so this statement is valid or not. So who takes the responsibility? So who will give this responsibility? So here the main concept is there, which is nothing but the logic. So logic will help you to understand the validity of a statement. This statement is valid or not. Who will tell you this? The logic. So logic is very, very important topic. You always try to understand this. Very, very important. Mathematical logic will always help you to understand, check the validity of a statement. Now, okay, sir, I understood that you are trying to say that the mathematical logic will always help us to understand the validity of a statement. Okay, sir, I understood. But give me a broad perspective. See, if you want to understand the broad perspective, so let's try to understand from a computer science point of view, what is the main intention of a computer science point of view? They are thinking that they are knowing the programming language and then they will create a software. So this is the perspective of a computer science student. The main perspective of a computer science students, they think that they have the programming language and then they will try to create the software, right? You will be having the programming language, and then from programming language you will try to create the software. But this is not just a computer science perspective. There are more than this. There is a very broad perspective. So in order to use the programming language, you should have the algorithm, and then you will try to implement this algorithm into PL, and then from PL you'll try to have a software. But in order to use the algorithm is basically a method. Okay, programming language is like a syntax. So you will try to use this method, you will try to implement into programming language, and from programming language you will be making your own software. But algorithm we directly cannot go and cannot use it. For example, suppose if I will tell you, can you make one software which tells me by taking the matrix representation and which can tell me whether this graph is having a perfect matching or not, right? Graph is having the perfect matching or not. Suppose, for example, suppose if we'll have a certain this type of software. For example, suppose if I will tell you, can you make one software where your input should be any type of graph and your output should be whether it contains a perfect matching or not. So when you will try to use some graph algorithm, and then suppose if you're using some graph algorithm, then you should also require some kind of theorem. So always remember, in algorithm, somewhere you will be requires a little bit of theorem. If you are making the software related to number theory, you will always require the theorem. If you are making a software related to mathematical tool, you will also require the theorem. Whatever the type of softwares you will be making it, you will require a little bit of theorems. So in whenever you will try to make the algorithm does not directly go and directly use it. Basically uses the theorem. It also implements theorem. But what exactly is a theorem? Theorem does not directly comes from a one direct type of statements. Theorem basically comes from a, theorem is basically comes from a conclusion, the set of statements which leads to the conclusion. So here there are different types of statements, and then there is one type of conclusion here, and then this conclusion will leads to what? This conclusion will leads to theorem. So for example, you will have the programming language. From programming language, you will make a software, and you will use that algorithm into programming language. And programming language, in order to use the algorithm, you will also require the theorem. But from where you are using the theorem? Theorem you are using where the multiple statements leads to conclusion, and then this conclusion you are using as a theorem. So sir, basically this is the broad perspective related to your computer science. But where is the mathematical logic? Okay, I understood that you are saying that here the theorem, mathematics has been involved, the algorithm has been involved, programming language is involved, and you are trying to make a software, so software is involved, and you are running this software on the hardware, so your digital logic COA operating system has been involved. So this is basically the broad perspective of a computer science. But where is this mathematical logic? Where, exactly we are using this mathematical logic. So now the mathematical logic, it gives us power. If anybody will ask what exactly is a mathematical logic, then you have to say that mathematical logic, it will gives us power to check the validity of a statement. For example, suppose if there is one theorem, you are trying to prove a theorem. So if you are writing this statement, so this statement is valid or not, the power is given by the mathematical logic. This statement is valid or not, this power is given by the mathematical logic. This statement is valid or not, this power is given by the mathematical logic. So I'm trying to tell you the whole perspective. If anybody will ask what exactly is a mathematical logic, you have to say that mathematical logic, it will gives us power to check the validity of a statement, whether the statement is valid or not. It gives us power to check the validity of a statement. So this statement is valid or not, this statement is valid or not. So who gives this power? The mathematical logic will gives us power to check the validity of a statement. Okay. Now let's move ahead. So, but sir, from where you are using this type of statement? So there is one set of English statement. So in 9th or 10th standard, you may have studied the different type of English statement. So there are so many different types of English statement. There is a exclamatory statement, there is a questioning statement, there is a ordering statement, there is a imperative statements. So in 8th or 9th standard, you may have your different type of English statement. So can I say that this is a set of all the English statement? Can I say that? Can I implement all the English statement into this type of statements? No, we cannot implement all the English type of statements into this type of statements. So we don't uses all the different types of English statements. We uses a very special set of English statements. Those set of statements are called as a factual statement. What is the meaning of a factual statement? They create a facts, whether this is right or whether this is wrong, whether this is yes or whether this is no, whether this is true or whether this is false. So they creates basically the facts type of statement. Okay, they try to create the facts type of statements. So we only take those type of statements and we uses into the mathematics. So always remember, in mathematics we do not dependence on every type of statements, we depends on a very factual statement. So what kind of factual statement? Factual statements are those type of statements which will have only two outcomes, either yes or no, either true or false, either 1 or 0. So any statements which is having only two types of outcome, yes, no, true, false, 1, 0, missile will go or not go. So this type of statements are called as a factual statement. So there are so many different type of English statements. For example, let's consider there is a questioning statement. If I'll tell you how are you, so we are not using this type of statements, we are only using the factual statements. So in mathematics, these factual statements are called as a, okay, these factual statements are called as a propositional statements. What we are calling this as, we are calling this as the propositional statement. So here we are having this, and then that is called as a propositional statement. So now let's talk about what exactly is a propositional statement. So here we are carrying forward this. So now this is called as what? This is called as a propositional statement. So if anybody will be asking what exactly is a propositional statement, you have to say that any type of statement, any type of English statement which will have the two outcome, whether we can say that yes or no or true or false, 1, 0, any type of statement which is having only two outcome, then those type of statements are called as a propositional statement, or which defines some facts. For example, my name is Satish Yadav. This is a one type of factual statement, whether this might be true or whether this might be false. This is a very simple statement which is called as a factual statement, right? So these propositional statements are basically, it is of two types. One type of statements are basically called as a simple propositional statement. I know that you may have studied this type of things, but still I'll try to give you more insight about it. Please listen. So this propositional statement is basically of two types of statement. One is called as a simple propositional statements, and then another one which is called as a compound propositional statement. So there are basically two different type of propositional statement. One is called as a simple propositional statement, and another one is called as a compound propositional statement. So there are two different type of statements, as we can see that here. So what is the difference between the simple and compound? If I will be talking about with respect to this, then I can say that the simple propositional type of statements are basically those type of, if I'm talking about simple propositional statements are those type of statements which you cannot break it, okay, which is not breakable basically. So simple propositional statements are those statements which are not breakable. Not breakable, what is the meaning of not breakable? For example, if you will break it, so there is no meaning into that. So if you try to break it, then it does not have any meaning, okay, it does not have any meaning at all. And for example, my name is Satish Yadav. So if you try to break it, then what will happen? It does not have any meaning. But compound propositional statements are those type of statements where you can break it into multiple simple propositional statements. For example, if I will write one this, 5 is greater than 3. See, this is one type of statement. Either this can be true or it can be false. So 5 is greater than 3. So if I'm writing this statement, this is a factual statement. So you can also consider this as the propositional statement. Why? Because it is defining either true or false. It is defining either yes or no. It is having only two outcomes. So if I'm writing something, either this can be true or this can be false. For example, what is a compound propositional statement? Compound propositional statement is 5 is greater than or equal to 3. So you can try to divide this compound propositional statement into two different type of simple propositional statement. One type of simple propositional statement, you can write 5 is greater than 3, or here you can write which is nothing but 5 is equals to 3. So if you try to understand visual representation of a compound propositional statement, so compound propositional statement, it is a type of propositional statement where you can divide into multiple simple propositional. So this is your compound, you can divide into two simple propositional statement. Now the doubt arises, see sir, it is necessary we have to divide into two simple propositional statement, so either S1 or S2, or we have to divide into multiple simple propositional statement. So there is a simple propositional statement this, there is a simple propositional statement like this, or there is another simple propositional statement. So see, it is totally depends on the compound. Sometimes you can divide into two simple propositional statements, sometimes you can divide into two or more, sometimes you can divide into three, sometimes you can divide into four. So it is totally based on your compound propositional statement. So for example, here this is your compound propositional statement. So when you try to divide, you divide at some point, that is called as your division point. In division, division point in propositional logics are basically called as the connectives. Your statements are basically based on your connectives. So this is called as a connectives. So for example here, see, as you can see that this is basically your connective. So this is your whole compound propositional statement. Now you can divide into two simple propositional statement, where the first simple propositional statement will be 5 is greater than 3. Second propositional statement will be 5 it is equals to 3. So this is your compound propositional statement. That is your simple propositional statement. This is your compound propositional statement, where this is your first simple, this is your second simple, and here you will be having which is nothing but OR. So this is called as a connective. We are having the different types of connectives, but majorly we are talking about, for example, 4 major connectives here, and the first one is your conjunction, and then second one disjunction, and third one is single implication, and here you will have a double implication. Okay, so you have basically 4 major different types of connectives. First one is a conjunction, second one is a disjunction, third one is a single implication, fourth one is a double implication. Now, okay, I hope that everybody has understood this slide. Please let me know that any doubt, then I'll move on. So we are having the different types of connectives. Now let's talk about what exactly is the different types of connectives. The first one, we are having this conjunction. Everybody knows about it. I'm just trying to give a little bit of brush up on this, and then we'll start the actual logic. Conjunction. Now, if I will be talking about this, conjunction is basically defining as your and, okay, or the representation it is having this. So when to use this conjunction? So that is nothing but the most, the important point. When we will try to use this, whenever you will see in English statement, whenever you will see the and, or whenever you will see the but, then we can use for conjunction. So now the most important thing, I'll try to explain you like this. See, there is one compound propositional statement, and then you will have a one simple statement here and one simple statement too. Now I will tell you the summary of whole propositional logic, and it's like this. We can only define the truth value, directly truth value, only for a simple propositional statement. We can directly define the truth value only for a simple propositional statement. So for example, here, this is your simple propositional statement. We can directly define the truth value of this. Directly define the truth value of this. This is another simple propositional statement. We can directly define the truth value of this. But if you will ask me, can you directly define the truth value of this compound propositional statement? Then I will say that no, I cannot directly define the truth value of compound propositional statement. And why? Because see, I do not have that authority to define the truth value. What exactly is a truth value? Truth value means you can define true or false, right? You can find out the value of that statement. Truth value means you will have two outcomes, either 1, 0, true, false, something like that. So again, I'll try to repeat it. I can directly define the truth value with respect to this statement only. I can directly define the truth value with respect to this statement only. I cannot directly define the truth value of this. So sir, how we can define the directly truth value of this? Directly we cannot do it. Indirectly we can do it. That means if I want to find out the truth value of this, then I will ask to this, okay, tell me what is your value. Then the compound will say that I do not have any value. Go and ask to the simple propositional statement. And that is why you will be having the, the table. So many times a student used to ask me, sir, what exactly is a table? Then I'll say that table is basically the case studies in order to find out the truth value of this compound. So now if I want to ask what is your truth value, then it will say that go and ask to this type of simple propositional statement. And that's the reason, for example, we are defining the variable for this, and here this is the variable p which has been assigned to one simple propositional statement, and there is another variable q which has been defined for another simple propositional statement. So for example, here we are having this, the truth table, and I will say that this will become p and then this will become q. Whenever you will see and or but, we have to use this conjunction, and then that is nothing but p and q. Now when the P and Q will, or how we can define it. Everybody knows about it. I'm just trying to giving a brush up, a more inside story about it. So for example, let's consider if this is true, then this statement will become true. For example, this is true and then this is false, then this statement will become false. If this is false, this is true, so this statement will become false. And if this is false, then this will become false. Now, one thing you people have to understand very clearly, and that is basically whenever if something is made up of your conjunction, or whenever if something is made up of your and condition, one thing you have to take care very easily, and that is when a compound statement is made up of two simple propositional statement, and if one of them is false, then it does not take care about this statement. What this statement is trying to say, that this whole thing will become what? This whole thing will become false. So this is a major breakthrough that you can understand with respect to the conjunction. Suppose if there is a compound propositional statement, and if it is made up of three simple propositional statement and one of them is a false, then what will happen? It does not matter what others are saying. Then it can say that the whole statement will become what? The whole statement will become false. Then we can definitely say that the whole statement will become false. So suppose if there is one compound propositional statement and which is made up of four different type of simple propositional statement, and one of them will become a false. Suppose even if it will become also false, then it does not matter what all others are saying, then again the whole statement will become false. So that means this whole thing will become false. So what you can have the assumption from this, you can have a very simple assumption. It says that key and hates false. So here I'm writing this statement, and this statement you have to understand, and hates false. Okay. So this is sometimes when we are reading about a quantifier, this is the basic of the quantifier. In quantifier also, I will try to teach you the same thing. See, I know that I have a trust on you, you know everything, but I'm trying to give you more inside story about it. Story like directly we cannot define the truth value or variable to compound propositional statement. That's a one side. Second insight, that and hates false. So this is the most important thing. See, I'm not trying to tell you that you have to remember this table, but I'm trying to tell you have to remember this statement, and that statement says very easily, and it says that and hates false. So it's a very simple and it's a very easy concept that you people can try to understand. I hope that this has been clear to each and everyone. Please tell me that. Clear?
Yes, sir.
Yes, sir.
Okay. Yes. Now we are having the second type of the important thing, and then that is called as a conjunction. Conjunction is basically your or condition, and we are having the two different types of or. Okay, one is called as your exclusive or. Exclusive or we are mostly learning into digital logic, and second type of or is called as your inclusive or. Inclusive or is related to your mathematics. So what is the difference between exclusive or and inclusive or? See, if I'm talking about exclusive or, it says that one or another, one or other, that's it. One or other, that is related to what? That is related to your exclusive or. See, if I'll talk about inclusive or, that says that one, other, or both. One, other, or both. So this is related to what? This is related to an inclusive or. So in mathematics, we learn more about inclusive or. So let's try to take one example related to inclusive or. So for example, here, suppose if I'll be talking about your truth table. So let's consider this is your P, this is Q, and then here you'll have a P or Q. Suppose if this is true, then this will become true. If this is true, this will false, then still this statement will become true. If this is false, this is true, still this statement will become true. And if this is false, this statement will become false. What you can understand from this point is basically, if at least one of the statement is true, then the whole statement will become true. Now, what we can have the assumptions related to this? Suppose if there is one statement which is made up of two simple propositional statement, and if one of them is a true, then what will happen? It does not matter what you are writing, then the whole statement will become true. Second assumption or second criteria, for example, suppose if your compound propositional statement is made up of three simple propositional statement, and if one of them will become a true, then it does not matter what the others are saying, then the whole statement will become what? Then the whole statement will become true. So here also, if your compound is made up of two simple propositional statement, and if one of them is a true, then true will see the or, then the whole statement will become true. Here, if your compound is made up of three simple propositional statement, and one of them is a true, then true will see the or, the whole statement is true. In a simple language, we can say that or loves true. Okay, so these two things you have to remember. Again, I am not telling you to remember the truth table. Everybody knows about the truth table, and here I can say that one or other or both. So for example, here as you can see that this is one, then again this statement will become true, or other, again this statement will become true, or here the both, then again this statement will become true. So we can say that P or Q will become true. So this is related to what? This is related to your conjunction. So this is the concept which is related to your inclusive or. So inclusive or says that one or other or both. What you can learn from this topic is basically or loves true. I can tell you one example so that you can understand more specifically related to this. So we have understood the concept of a dominating set, if you'll remember that. So dominating set says that either the vertex directly belong, directly belongs, or its adjacent will belong, or its adjacent belongs, right? So here we are having this statement. So I hope that everybody remember that. Now as you can see that this statement is, this is your first simple type of propositional statement, and this is the second simple type of propositional statement. So this will become P, this will become Q. Now you can understand the power of mathematical logic. Suppose if somebody has given the domination number statement in some research paper, and if you are reading this domination number research paper, then you are saying that the first definition, domination number says that either the vertex directly belong or its adjacent will belong. So you will try to prove it by the truth table. This is P, this is Q, and then this is P or Q. This is your statement. Okay, this is P or Q your statement, or this is your theorem, which is nothing but P or Q. Now what will happen? Suppose if a vertex directly belong, that means if this is true, then still you can consider your statement is also true. For example, if the adjacent will belong, if the second statement is also true, still you can say that your theorem is, your statement is true, right? Still you can say that your statement is true. For example, suppose if the vertex directly belong and its adjacent will also belong, then still you can say that your statement will become true. So in that matter, this is the actual implementation. This is the actual, you can say that the representation or the actual thing related to this. Understood, everyone? I think in the main topic I have given that conjunction, disjunction. Okay, this is disjunction. Sorry. Thank you for pointing it out. Okay.
Okay, sir.
The next one is very important, and then that is related to a single implication. See, what exactly is a single implication? See, the whole gate questions revolves around this operator. If you will understand the truth table of this operator, then you can understand all. And then this is related to what? This is related to your single implication. Single implication, sometimes it is also called as a conditional statements. Conditional statement. Either you can call it as a single implication, or you can also call it as a conditional statements, or you can also call it as a single conditional statements. The whole gate questions revolves around this. Even the most of the theorems, okay, most of your theorems are also revolves around this. So the way you understand this, if you will understand thoroughly, or if you will understand in a good way related to this single implication or conditional, then you can consider that 30% of your job is done. You just have to go through a little things related to that. So here we will have the single implication. Either you can call this as a single implication, or you can also call this as a conditional. Now, what is the representation of this? The representation of this is something like that. The first thing, that when we have to use a conditional statement, when we have to use a single implication, We have to use a single implication. We have to use this notation. See, everyone try to understand. We have to use this notation, and when you will see something like that, or either you will write like this, or you can also try to write like this. When we have to use this notation, we have to use this notation. First thing, if you will see any statement that contains something like this, if P then Q, then you have to use this statement. Another one, if P comma Q, then you have to use that statement. Or Q if P, then you have to use that statement. Or whenever you will see, you have a different types of this, whenever you will see this statement, you do not have to do anything. Whenever you will see this statement, you have to use P implies Q. Whenever you will see this statement, if P comma Q, then you have to use this statement. Here, Q if P, whenever you will see this statement, you have to use P implies Q. I mean, this statement. Q when P, or whenever you will see P implies Q, then you have to use this statement. You do not have to do anything. You just, whenever you will see this, you just have to use this. Whenever you will see this, you just have to use this. So if P then Q, then you have to use P arrow Q. If P comma Q, then you have to use, this statement. Q if P, then you have to use this. Q when P, then you have to use this. P implies Q, then you have to use this, right? So you have to use this whenever you will see something like that. Or whenever you will see Q unless negation of P, then again you have to use this. I will give you the different types of things. Okay. So there are different. So if P then Q, Q if P, Q when P, or Q whenever P, or Q whenever P. Whenever you will see this type of statements, you have to go and you have to use this type of things, which is nothing but P implies Q. So if P then Q, whenever you will see any of these things, you just have to use this. Now let's try to understand the truth table. Once you will understand the truth table, the major things are over. And how we can try to use it? Let me take one example. First, I will teach you with the help of one example, and it will be very important. It will become very easy once you will understand with the help of that example. And your example is something like that. For example, if I'm writing, okay, if perfect matching exists, okay, if perfect matching exists, okay, then number of vertices will become even. Then number of vertices will be even. Then number of vertices will be even. Number of vertices will become even. Number of vertices will be even. So if perfect matching exists, then number of vertices will become even. So let's consider that this is nothing but your statement. Let's consider this is nothing but your statement. If perfect matching exists, then number of vertices will become even. So as you can see that how to identify these things. So as here you can see that it is starting from which statement? It is starting from if. So if any statement starting from if, either you can go with respect to the first one or you can go with respect to the second one. So I'm going with respect to the first one. Why? Because here, as you can see that this is nothing but your first operator, and then you'll have the then, and then here you will have the second operator. So for example, I can say that this is nothing but your P, and then this is nothing but your Q, right? So let's try to understand related to this. So if perfect matching exists, then number of vertices will become even, right? Suppose if I want to make a truth table of this, as I'm telling you, understanding the truth table of this will always be helpful. It will solve most of our major problems related to your logic, related to your mathematical logic. So what it says ki if perfect matching exists, then number of vertices will always become even, right? So if perfect matching exists, then number of vertices will become even. Now, suppose how to draw the truth table of this. Please try to focus. For example, suppose if you are a new mathematician and you have given this a brand new theorem to this whole world. Okay, suppose like this theorem or any other theorem or something, some different types of theorem. you have given a very brand new theorem to this world. And what is that theorem? The theorem says that if perfect matching exists, then the number of vertices will be even. You have given this theorem to this whole world. So suppose if you have given this theorem to this whole world, then what will happen? The people will come and people will try to destroy the theorem, right? That's how the mentality. So let's consider there is a 4 different type of people, and then they are trying to come and then they're trying to destroy your theorem. So first person. So what are the cases? Let's take all the cases. Your cases, maybe in some graph perfect matching is existing, and let's consider that because there, with respect to any one statement, you will have a 2 possibility. First possibility, perfect matching is also existing, even number of vertices are also there. For second possibility, perfect matching is existing, second, even number of vertices are not there. Third possibility, where the perfect matching is not existing and even number of vertices will be there. And then the last possibility, where the perfect matching is not existing and then the even number of vertices is also not there. Let's consider you will have a 4 different types of possibility. Let's consider the first condition, perfect matching is existing. So here this is the first person, and you have given a brand theorem, and then there are 4 people, there are 4 mathematicians. So the first mathematician is coming, and then first mathematician is coming with one example where he is saying that I'm having a one graph where the perfect matching is existing. That means this is true. The first one is true, and the even number of vertices are also getting true. So that means this person is saying that true implies true, and then you will be getting as a true, right? This is the first person. So what this first person is doing? The first person is doing where the perfect matching is existing. So he is considering that the statement is true, right? He is considering that the statement is true. And then second point, where the even number of vertices are also true. So true implies true, and your answer you are getting is basically true. Now let's talk about the second person. Now what will happen with respect to the second person? Second person says that there is a graph where the perfect matching is existing, but the even number of vertices are not existing. See, everyone is trying to destroy this theorem, and I can bet on that this theorem will only be destroyed at this point only. That means if the first statement is true and the second statement is false, then only the whole statement will become false. Then only your theorem is false. Why this is called as a conditional statement? Why it is called as an implication? Because you are telling to the whole world, you come up with any example where if the perfect matching is existing, because you have given this theorem and you're telling to this whole world, you come up with any example where the perfect matching existing. If the first condition is existing, then 100% the second condition will exist. You are giving a condition to each and everyone. That is why it is also called as a conditional statement. You are giving a condition to each and everyone. You are saying that if this condition met, then the 100% the result will be like this. So you have promised this to everyone. Now what happened? The second person, second mathematician, he satisfied the first condition, but here the second condition is not existing. You try to consider, for example, this is already a theorem. Okay, everybody has proven this is theorem. We are considering one example where the, just hypothetical example, where the first condition is existing, first condition is getting true, but the second condition is not getting true, but the second condition is getting false. So that means if the first condition is going to be true and if the second condition is going to be false, then only we can say that the whole statement is false. Otherwise, we cannot say that the whole statement is false. You understood these 2 points? Please let me know. Let's talk about the third statement. What is this third statement? Third statement will give you more clarity related to it. So, for example, suppose if you have given this statement, you have given one conditional statement, and what this conditional statement is trying to say that if perfect matching exists, okay, but here see this is saying that this statement is false. That means you have given one condition, you're telling to this whole world if perfect matching existing, but this person is come up with one example where the perfect matching is not existing. That means, can I say that this person is coming with the wrong example? Yes. You're promising first you show your perfect matching exists. First you show your perfect matching exists, then I will tell you number of vertices will become even. But this person is coming up with wrong example. So if anyone is coming up with the wrong example, can I say that my theorem is wrong? No, my theorem is not wrong. Your example is wrong. So that is why if the perfect matching is not existing, but for example, suppose if the number of vertices are even. Okay, let me take the another example where here the perfect matching is not existing, but the even number of vertices are there. So I can say that my theorem is true. I cannot discard my theorem. My theorem will be true. So that is why if the false implies true, then only we can say that the whole statement is going to be. In the same way, suppose if this is also going to be false and if this is also going to be false, so that means if my first thing is going to be false, then I can say that the whole statement is going to be true. Whole statement is going to be true means my theorem is true. I cannot say that my theorem is wrong. So this is the most important thing. And out of that, the whole summary is basically when the something is false, then it does not matter what you are writing on this second point, then the whole statement will become what? The whole statement will become true. So anywhere we can say that the false will always imply, if something is false, false implies anything will always become a true. Why it is happening? The false is implying. That means if the false is implying, it says that you are taking a wrong example. So if you are taking a wrong example, then you cannot say that your statement, you cannot say that your statement is wrong. So if this is going to be false, that means if this is the wrong example, taking a wrong example cannot disprove your theorem. So this is the most important thing which is related to this. Understood, everyone? No, it means whenever your first statement is false, then we do not have to worry about the theorem. Okay, I'll try to explain you more related to this. For example, here, if G is planar, then E is less than or equal to 3n minus 6. Right? I give this theorem to each and everyone. What student used to give me the answer, right? They are saying, sir, take K33 and tell me, sir, for K33 it is not something like that. Bro, I gave you this theorem and this theorem is saying that if G is a planar, you're coming with one example where this will become what? This is your false. That means if the left side will become false, still my theorem is true. You cannot disprove my theorem based on the wrong example. You cannot disprove my theorem based on the wrong example. This is a wrong example with respect to this. I'm telling you, take a planar graph, then we'll talk about this. Then I will prove it E is less than or equal to 3n minus 6. This is my theorem. And you are coming up with one example where the K33 is non-planar. I'm trying to tell you, take the first statement as a true, then we'll talk about E is less than or equal to 3n minus 6 or not. I'm trying to tell you something like that. I'm saying that take G is a planar, and then we'll talk about E is less than or equal to 3n minus 6. But you're coming with one example where K33 is non-planar. You take any planar graph, then I will show you E is less than or equal to 3n minus 6. So if I'm confident about this, okay, then what will happen? The most important thing that you can understand is, if you have come up with any planar graph, but I'm unable to prove this, E is less than or equal to 3n minus 6, then I can say that my theorem is wrong. My theorem is only wrong at one point of time if I have promised left side is true and I'm saying that right side is false, then only this will become false. Then only it will become false. Otherwise, it will never become false. If I'm taking the first statement as a true and then the second statement will become a false, if you'll have a condition like this, then only you can say about with respect to false. Otherwise, you cannot say like that. Okay, so there are three different versions related to your implications. For example, if I'm writing the perfect matching is existing, the number of vertices will become even. So there are three different versions. First one, which is called as a converse, or it is also called as a vice versa. and here you will have this inverse, and the third one which is called as a contrapositive. There are three different variations. Now today I will prove you why, when I was teaching you the planarity at that point of time, I told you ki this one is equivalent to contrapositive. Today I will show you. For example, perfect matching existing even number of vertices. Let's consider this is P and then it implies Q. It is called as a vice versa, or it is also called as a converse. Now, what exactly it will become? It will become Q implies P. What is the Q? Q, if you will say that, it says that if any graph is having even number of vertices, can we say that the perfect matching is existing? If any graph is having even number of vertices, can we say that the perfect matching is existing? No. That means we can say that P implies Q is not equivalent to Q implies P. We can easily say that the P implies Q is not equivalent to Q implies P. That is related to your first statement, which is nothing but your converse. If I'm talking about with respect to inverse, inverse says that negation of P will implies negation of Q. So you have to take the negation of the first side and then it will imply negation of Q. Now, if I will be talking about with respect to this, what is your negation of P? Negation of P means negation of perfect matching. So it says that if there is no perfect matching in any graph, there would not be any possibility of even number of vertices. Can I say that this is also same as the first one? Can I say that this is also same as the first one? What is your opinion on this? It says that if there is no perfect matching in a graph, then there would not be even number of vertices. Arey bro, wrong. See, here is no perfect matching, but I can show you the number of vertices are even. Getting my point or not?
Yes, sir.
So that is why this statement is also going to be false. I mean, this statement is also not same as this. So P implies Q is not same as negation of P will implies negation of Q. Let's talk about the contrapositive. What the contrapositive says that? Contrapositive says that P implies Q is same as negation of Q will implies negation of P. But what exactly is the negation of Q? What exactly is the negation of Q? Negation Q. What is Q? Q is even. That means if there is no even number of vertices, then it implies there is no perfect matching. So if it does not have the even number of vertices, what is the meaning of that? That means it will have, suppose if it will have the odd number of vertices, then there would not be any perfect matching. So there is no perfect matching. This, which is true. So that is why we can say that this statement is going to be same as this. Understood, yes or no?
Yes, sir.
Can I say that the converse and inverse are same basically? Arey,
Yes,
that is the
sir.
same thing. Converse and inverse are
Contrapositive
basically
only.
same. Yes or no? I can also try to prove with the help of this truth table. Okay, let me do it fast. So here you'll have this P, this is Q, and then this will become P implies Q. This is negation of Q, this is negation of P. And let's consider this is negation of Q implies negation of P. Now here, this is true, this is true, this is true, this is false, this is false, this is true, this is false, this is false. Now P implies Q, this is true, false, this is true, and then this is true. Q, negation of Q, this is false, this is true, this line. True will become false, false will become true, and true here will become false, false will become true. Negation of P, here you will get false, this you will also get false, and false will become true, and then false will become true here. Now, negation of Q will implies negation of P, negation of Q will implies negation of P, this will become true. True implies false will become false. False implies anything will become true. True will implies anything will become true. So, as you can see that in truth table, two columns, if the two columns are equivalent to each other, then we can say that they are logically equivalent. So I don't think you'll have any problem to this. What I'm trying to tell you that suppose if A is okay, suppose if A is logically equivalent to B. Suppose if your A is okay, just try to understand. Suppose if your A is logically equivalent to B, when your A is logically equivalent to B, that means another way of understanding is basically this is your column A and then this is your column B. Then what will happen? Column A and then column B both will have the same value. Another way of writing ki A and B will have same values. Can I write like this? They will have the same values. So A and B will have the same values. A will have the same instance. Whatever the values of A, the values of B will be there. See, for example, whatever the values of A. So suppose if the values of A is also true, then the value of this is also true. Another way of writing, ki A and B will have a same behavior. A and B will have same behavior. A and B will have a same behavior. What is the meaning of A and B will have a same behavior? Same behavior means suppose whenever A is true, B is true. Whenever A is false, B is false. Whenever A is true, B is true. Whenever A is false, B is false. That's the meaning of same behavior. As you can also say that if this is A means this column, that means P implies Q. B means negation of Q will implies negation of P. Whenever this is true, this will become true. Whenever this is false, this is false. Whenever this is true, true. Whenever this is true, this is true. That means they are having the same behavior. A and B will have a same behavior. So whenever two columns are same or two things are having the same behavior, then we can say that they are logically equivalent to each other in mathematics. Okay, then we can easily say that they are logically equivalent to each other in mathematics, which is very, very simple. Try to read this question and try to tell me the answer related to this. I hope that everybody can read it. Right? Okay. Tell me the answer related to this. What is the answer for the first one?
Contrapositive.
Contrapositive.
Okay. For the second one?
Inverse.
Inverse.
Third one?
Contrapositive.
Fourth one?
Inverse.
Inverse.
And E?
Converse.
Converse. Okay. I don't think you need any type of explanation. So shall we move ahead?
Yes, sir.
Yes, sir.
Option E.
What it is trying to say that the converse of the inverse. So first you try to divide. Option A. I'm explaining the option.
E. Elephant.
Okay, E. What it is trying to say that the contrapositive first you have to try to divide it. It says that contrapositive of P implies Q. So here this is P implies Q. Contrapositive of P implies Q will become negation of Q will implies negation of P. Now it says that take an inverse of that. So let's go to inverse. Where is that inverse? Inverse says that whatever it has been written, take negative of both. For example, suppose if something is like this, for example, if something is A implies B, then negation of A will implies negation of B. This is called as the inverse in a simple term. So here, negation of Q will implies negation of P. Inverse of this, negation of Q will become, negation of the first one will become Q, negation of the second one will become this. So it will become Q implies P. So now what is Q implies P? So the inverse of the contrapositive of P implies Q, this will become the converse of P implies Q. Understood now? Clear?
So can last question answer also be inverse because they are logically equivalent?
No, it is converse now. Because if you will take with respect to this, it is converse.
Okay, yes.
The contrapositive of P implies Q, contrapositive of this is this, and then you have to apply inverse. So inverse of this is this. So this will, what is this of this? This is the converse of this, na?
Got it.
Now there is a one more concept, and then that concept is called as a double implication. Either you can call it as a double implication, or it is also called as a biconditional. Biconditional. So either you can call it a double implication or biconditional. Biconditional is having some representation, and that representation will be something like that. That means it is going from left to right also, and then it is also coming from right to left. So left to right is also there, right to left is also there. Now, what it says, so whenever you will have this P, and then whenever you will have Q, and then it says that P double implication Q, that means if this is true, then only this will become true. If this is false, then only it will become true. So that means whenever you will have the bi implication, whenever you will have the biconditional, it will be only true when both will have the same behavior. That means when both the true, then only it will become true. When both the false, then only it will become true. Otherwise, it will not become a true. So let's take one example. Or when to use the biconditional. Whenever you will see any statement where it consists of if and only if, then only you have to use this condition. Or whenever you will see something like that. So whenever you will see something like this, if and only if, then you have to use the biconditional. Or whenever you will see if, then only you have to use the biconditional. So biconditional you have to use when you will have a something like that. For example, suppose if it is true and then if it is false, then the whole statement will become false. If this is false and if this is true, then the whole statement will become false. So can I say another way of writing ki in double implication, what is the requirement of this? In double implication, the requirement of this is basically it should have both same behavior. Can I say like that? Yes or no? Can I say it should have a same behavior? Okay, let's take one example so that you can understand in a better way. For example, when I was teaching you about graph theory, there I taught you Eulerian graph. So any graph is a Eulerian. There you can see that I have used if and only if. There I have used the concept of if and only if degrees of all vertices are even. Degrees of all are even. All are even. When you will try to see that when degrees of all are even, then when this will become a true, when your graph is Eulerian, then only all degrees are even. So when the first one is true, then the second one is true. Why it is happening? Because we have used if and only if. Suppose if this is going to be false, suppose if your graph is not Eulerian, then 100% the degree will also not become even. Can I say here? Both the conditional, biconditional. Understood, not understood? Okay. Now, one more thing you have to understand. Suppose if there is a is logically equivalent to B, and whenever if logically A is logically equivalent to B, so here first condition, when your A is logically equivalent to B, and this is your A, this is your B. So suppose if A is logically equivalent to B, that means both will have a same behavior. And if I will use double implication here, then what I will get? If suppose if this is true, you will get this is true. If suppose this is false, again you will get true. If suppose this is true, again you will get true. If suppose this is false, again you will get true. So can I say that all the instance of a double implication will become true? So if at any point, if all the instances are you are getting true, then that expression is called as what? Is tautology. That expression is called as what? That expression is called as a tautology. Simple, understood? Yes or no?
Yes, sir.
So, logically equivalent will have three different type of definition. First, A logically equivalent B. Another way of saying that A and B are having same behavior, are having same behavior. A and B are having a same behavior. Or the third one, A double implication B is tautology. Can I say that all these three expressions are same? First expression is equivalent to the second expression. First statement is same as second. Second statement is same as third. Third one is same as first. These all are equivalent to each other. Either you will write like this, or you can also write like this. A double implication B is a tautology. What is the meaning of this? That means A and B are logically equivalent. That is why you are getting a tautology, na? If A double implication is a tautology, that means you will get the same value for all. So if the third expression is there, then third expression will also imply A double implication B. What do you say? What do you say? Please tell me fast.
Sir, if A implication B is a tautology, then if A is false, then B is also false. Is it possible?
Yes. Take example. If your graph is not Eulerian, what you can say about the degrees of all vertices are even? See, it's a very simple. If your graph is not a Euler graph, when your graph is not a Euler graph, when your graph is not a Euler graph,
If it doesn't cover
some
all the
vertices,
edges.
some vertices are not, no, some vertices are not even. That is why your graph is not Euler graph, right? So if your graph is not Euler graph, then we can say that our degrees of all vertices are even. Then again, if this is false, this is false.
Yes, sir, clear.
Clear? I hope that this has been clear to each and everyone. We are having the different types of tables. Okay, let's discuss about all the different types of tables here. So for example, suppose if there is any table where the last entities everything is a true, if the last entities everything is a true, this expression is called as a tautology. This expression is called as a tautology, or sometimes it is also called as a valid expression or valid statement. Suppose if the last statement everything is a false, if this is false also, this is false also, this is false also, this is false also, this expression is called as a contradiction. Contrapositive is different. Do not get confused. This is called as a contradiction. Contrapositive is a different. For example, suppose if there is any expression where at least one is true. Suppose if there is any expression where at least one is true, at least one true. Suppose if any expression where this one is at least one true, any expression at least one true, then this expression is called as a satisfiable expression. Satisfiable expression. Try to understand this. For example, I'll show you. See, okay, try to see this table here. In this table, the last expression here, as you can see that at least one is true. So can I say that P and Q is a satisfiable expression? Can I say that P and Q is a satisfiable expression? Yes or no?
Yes, sir.
Right? P and Q will satisfiable expression. Did you understand what exactly is the meaning of satisfiable expression? Yes or no? Please let me know, everyone.
Yes, sir.
Right? Okay. Suppose if everything is a true, that means if everything is a true, that is called as a valid, or that is called as a tautology. Or you can consider as a, this is a school of boys, where school of boys school, everyone is boy, true is a boy. This is a school of girl. This is a school where in that class at least one boy is there. For example, suppose if this is expression where it is not a tautology, where it is not a contradiction, it is a mixture of all. Suppose if it is not a tautology, that means you will get at least one false. Suppose if it is not a contradiction, then at least you will get one true. So this expression is called as a contingency. What it is called as a contingency. So here, this is my first statement. Can I write all contingencies are satisfiable? What is your opinion? all contingencies are satisfiable. All contingencies are satisfiable. What will be your opinion on this? All contingencies are satisfiable. Can I say it is true or not?
True.
So,
This is true or false? What is your opinion on this? Can I write all valids are satisfiable? All valids are satisfiable. This is true or false? All valids
True.
are satisfiable.
So true.
yes.
Can I write all satisfiables are contingency? All satisfiables are contingency. What is your
No.
opinion on this?
No.
No. Also.
No. False. All satisfiables are not contingency. All contingencies are satisfiable. All valids are also satisfiable. I hope that this slide is clear to each and everyone. See, for example, suppose if I will give you any expression and you tell me whether it is tautology or not. A and if I'm giving any expression here, you tell me whether this expression is a satisfiable tautology or not. Tell me with the help of truth table or any type of method. Try to use any method you want to use and tell me whether it is a tautology or not. This expression is a tautology or not. What is the meaning of this expression? That means at the end you have to come up with one concept where everything will become true. I know that everybody has used the truth table. What you people may have done. I mean, what was the question? Let me tell you the question. The question was nothing but you have to check whether this is a tautology or not. So what you may have done, you have taken A, you may have taken B, you have taken C, and then later you have done A implies B, and then what you may have done, A and then A implies B, and then later you may have find out B implies C, and then you have written everything, and at the end what I have asked is basically is nothing but this is A and then A implies B and B implies C, and then the whole expression it is implying C, right? I'm asking whether this one is a tautology or not. So that means if all the expression this is coming as a true, then we can say that it is a tautology, right? Okay, I'll teach you the shortcut related to this. So it has been seen that this type of questions, there are so many type of questions related to this type has been seen into GATE examination, and I will teach you the shortcut, and then shortcut is something like that. For example, in order to teach you shortcut, what I'll try to show you the truth table of the implication. This is the truth table of implication, and you tell me where it will become a false. Where it will become a false.
Sir, if that whole bracket inside is true and the C is false.
Right? If your left side is a true and if your right side is a false, this is the only case where it is becoming a false, otherwise it is not becoming a false. Am I right, everyone? When your left side is a true, and your right side is a false, okay, when your left side is a true and your right side is a false, then only it will become a false, otherwise it will not become a false, otherwise it will never become a false. So what I'm trying to tell you, for example, suppose this is nothing but my expression. Suppose if I will try to check on that condition only, if I will try to check on that condition, suppose if I will consider this left side as a true and if I will consider the right side as a false, suppose if I will check, because this is left side, this is right side, if I will check on that conditions only, and if it converts as a false, then I can say that it is not a tautology. But if it will deny, then I can say that it is a tautology. Do you understand what I'm trying to tell you? Say yes or no. Then I will
Yes,
explain
sir.
in more detail. For example, see, suppose if there is one person, okay, and if this person is honest, if there is one person and if this person is honest, and if I will put a pressure on this person, suppose if I will put a pressure on this person, and if it changes, then that's not the honest person. Honest person will never change based on the scenario, based on the situation. If suppose if this is the person, and if you will force on this person, I mean if the society put a pressure on this person, and if this person is an honest person, this person will never change. What I am trying to tell you, if any expression, if this expression is a tautology, okay, for example, if this expression is a tautology, whatever I will do, can I say that it will change? No, it will not change. And you have also find out that it's a tautology. You have also find it out that it is a tautology. Now, whatever I will do, it will never change. But what will happen? It will change. So, my whole point is, try to understand this. My whole point is, I will try to make this statement as false. This statement as false. I will try to make this statement as a false. Right? Suppose if it changes as false, then I can say that it's not a tautology. Then I can say that it's not a tautology. It's not a tautology. But suppose if it denying of what? Suppose if it will deny, it will not change. Suppose if it will deny, then I can say that it is a tautology. Suppose if it is denying, then I can say that it is a tautology. Okay, let's try to understand the same statement here. So what this statement says, that this is A and A implies B and B implies C, and then the whole expression, it is implying C. So this method is limited only. Okay, this method is limited. So that is why I'm trying to first explain this method. Later for other questions, you will have another method. So for example, what we have to do? You have to check for a false. So this method is applicable whenever you will have any expression which contains the implication and they are asking for tautology. So this expression, this method is only for that. So what you have to do, you have to take the left side as a true, you have to make right side as a false. Now here, I am trying to take the left side as a true and I am trying to take the right side as a false. So if I am trying to take the left side as a true and if I am trying to take the right side as a false, so here I got the value of C as a false. So I got the value of C as a false. Now let's everyone try to understand. If I want to make the left side as a true and it is made up of and a condition, so it says that means this must also be true and then this must also be true and then this must also be true. So that means if A is going to be true, see, I got the value of A as a true. So here the value of A I got as a true. Now everyone please focus. See, this whole thing is a true. I got the value of A as a true. Now this whole bracket is demanding true and I got the value of A as a true. Then what should be the value of B? The whole bracket is demanding true. The whole bracket is demanding true. I got the value of A as a true. What should be the value of B? The value of B has to be true. So again, I got the value of B as a true. Now, and I got the value of B as a true. But what is the value of C, bro? Value of C is false. So true implies false will become false. Now false will see and hates false. What will happen? The whole left side will become false. And if the left side is a false and false implies anything, the whole statement will become true. So I was trying to prove this as false, but it turns out to be what? It turns out to be a true.
Sir, is this also called proof by contradiction?
Yeah, you can consider like that. Basically, it is a proof by contradiction. Okay, so here we'll have this. Try to see this question. I'll try to solve one. You'll try to solve by yourself. Okay. Okay, I want you to give a, okay, this is true and this is true and okay. For example, first you try to solve this. Once you will become handy, then I will give you more liberty to solve all the questions. Okay, try to solve this first, second one. I'm talking about second one. See what you have to do. See, it's a very simple. You have to take the left side as a true and you have to take right side as a false. I know that it is the second time you are not able to solve this, but I will help you to solve this. See,
So
the
not a
main intention,
tautology.
okay, fine. The main intention to solve this type of question, try to find out the values of variable. See here, first, I know that this is the first time. Believe me, after solving 4 or 5 questions, everyone will become professional into this. Now, try to consider the left side as a true. Here I have taken this as, this is whole left side, this is whole right side. So, the main intention is always try to find out the values of each and every element. So, here this is true. So, it contains a large amount of variable. I'm not going there. My right side is a false. This whole bracket I need false. Inside bracket you will have OR condition. So what should be the value of Q and what should be the value of S?
Both are false. Both are false.
What should be false? That means the value of Q should also be false. Value of S should also be false. That means the value of Q must also be false and value of S must also be false. Now for example, what are the values we are getting? We got the value of Q and we got the value of S. So here this is your S. Now this whole bracket needs, because see this whole left side is a true, that means, and it is made up of AND condition, so that means this bracket must also be true, this bracket must also be true, and then this bracket must also be true. Now try to understand, we got the value of S, so here the value of S is false and then the whole bracket is demanding true. What should be the value of R?
False. False.
False. So here, as soon as you are getting the value, write down as it is. So value of R is false. Where is R? R is here. So as soon as you are getting the value, try to substitute it. This whole bracket is demanding true. What is the value of R is false. What should be the value of P then?
True.
True.
True. The value of P must be true. So here I got the value of P as a true. Now, so value of P we got as a true. What is the value of Q? We already got it, so we don't need to find it out. True implies false. This will become false. False will see and hates false. So the whole left side will become false, and false implies anything will become true. Hence, second one is a tautology. Did you understand now?
So it is not a tautology, or
It is a tautology, no? Sorry, it is a tautology because it is denying. So the whole left side will become false. Okay, again I will try to tell you. This false will see and. So the whole left side will become false, and false implies anything, and then the whole statement will become what? The whole statement will become true. So it is a tautology. Did you understand? Do you want me to discuss the previous method or the method that I have taught you? Because that method is totally based on one concept, and then that is related to your type 1. Okay, that is exactly related to what? That is exactly related to your type 1. So there are basically 6 different types of method that I will teach you into your mathematical logic. So only one type we have covered, and there are type 2 is there, type 3 is there, type 4 is there. So there are so many different types of things will be there. So let's talk about the other type. But before asking about the other type, before asking about the other types, you tell me whether did you understand everything related to type 1? Okay. Is it visible, everyone? This
yes, sir.
question is
Yes,
visible?
sir. Visible.
Right.
Yes,
Right.
sir.
So in this, we have to use the type 1, and see if the question they have given that you have to go and you have to use type 1s, and obviously we are not able to, if even if you will use the truth table, then what will happen? It will take a large amount of time. So even if you use the truth table with respect to P, then it will take a large amount of time. So obviously we do not have to go and we do not have to use the truth table, because if you'll be using a truth table, then ultimately it will be a problematic thing. So that is
Sir,
why we
for
will not be using the truth table
3 or
anywhere.
more than 3 cases, it becomes large.
Yes. So if you'll see the answer, so this one is going to be valid and this one is going to be valid. And this is not tautology, this is not tautology. I hope that everyone got the same answer.
Yes, sir.
Yes, sir.
Right? And let's talk about, this is our second type of I can say that second type of gate questions here we are having.
So that's the answer
So
B.
with respect to this,
Yes, sir.
let's try to go and let's try to find it out which one of them is not a tautology. They are saying that. And here if you will see, you can get a different type of cases. I mean, this is your tautology, this is tautology, this is valid. If I will take this is true, this is false, this is also tautology, I think so. Yes, the answer is true and false. Yes, this is answer. This is not a tautology and this will become your answer. If you want, I can also solve it for you.
Sir, please solve, sir.
Do you want me to solve?
Yes, sir.
Yes, sir.
See, for example, if you will see this question, so in this question, little bit you will be having the cases has been expanded. So for example, if I'm writing this equation here and then I will write, which is nothing but A implies C, and then this whole thing is implying, and then this one is negation of B, and then negation of B, that will implies, which is nothing but A and C. So here we will be having some equations like that. Now let's try to understand. So for example, as you can see that, what is our main motto? Our main motto is we have to take the left side as a true and we have to make the right side as a false. Now if I will try to take this statement as a true here, and if I will try to take this statement as a false here, now it has to be clear that this must be true and then this must be false. Now as you can see that, if for example, suppose if you are starting from the left side, then left side A implies C is true, you are getting three cases. So I will not involve in anything that will be having a three cases. So this is the first thing you should understand. You should not involve at any point of time where it will be having a three cases, because it will take a lot of time. So obviously I will not starting from this, because A implies C, it is true. For example, this is A, this is C. So when the whole statement will become true, when this is true, this is true, when this is false, this is true, when this is false, and then this is false. So basically A implies C is basically true at three particular cases. That means both can be true. This is one particular case. I mean, first one is a true, second one is a true, first one is a false, second one is a true. This is the second case. And then the third case you are getting, the first one is a false and second one is a false. So A implies C is true. Basically, it will be having a three cases. So obviously, we are not going to involve into that. Okay, that will be for sure. We are not going to involve at any point of time with respect to this. So that is not a case. If you'll see it directly, so here we can say that negation of B, it is saying that it is going to be true. So definitely we can say that the value of B will become what? Value of. So our main motto is to find out the values of any particular element. So immediately we can say that immediately the value of any particular element will become anything. Here we are getting the value of negation of B will become false. Now we have to come up with one. It is totally based on experience. Just try to understand. For example, we are only getting the values of B. I mean, see, negation of B, we are getting this as true. So the value of B we are getting is basically false. A implies C is basically true. So this is A, this is C, this is true. That means this is true. This is false, this is true, and then this is false, and then this is false. So A implies C is true at the three cases. While here we are having this A and C. When the A and C will become false, A and C will become false at three cases. That means the first one can true, second can false, right? Or another one, for example, try to understand like this. When your A can be false and C can also be false, And when your A can be false and then C can also be true, or the third case that you'll have is key both can be false. I mean, which we have already seen it. Okay. The other case, this first one can true and second can false. Now, if you will try to understand very clearly, we can take this particular case. See, either you can take this particular case or you can take this particular case. So, for example, if I will put the value of A as a false and if I will put the value of C as a false, then the left side will become true, right? As everybody can see that if you will put the value of A as a false, so it will become false. If you will put the value of C as false, so it will also become a false. So false imply false, you will get this as true. That means this thing will become true. Now here if you will see that A and C, what will happen? Both will become full, both will become false. So if you will try to draw the truth table with respect to the truth table, at the end you are getting this as false. So we just have to find it out with respect to only one particular case. If something is a false, then that statement is not a tautology. So very specifically, we can consider one particular case, and with respect to one particular case, we can take this. Understood? Did you understand what just now I explained you? See, for example, let's consider that this is nothing but your truth table. And if this is nothing but your truth table, and suppose if you're getting the last answer is a false, you tell me that this expression is a tautology or not a tautology. This expression is a tautology or this expression is not a tautology. Yes. So even if you will see a single false over here, then what will happen? We can say that this expression is not a tautology. This expression is not a tautology. Then this will become very simple, right? This expression is not a tautology. Now you try to understand this expression here. Again, I will try to go and I will try to write down this with respect to this. See, for example, what we have to do? We have to take the left side as a true and we have to take the right side as a false. So when you want to take the left side as a true and when you want to take the right side as a false, so we are taking the left side as a true, we are taking the right side as a false. If you will go with respect to the left side, A implies C, it is true, then it will have a three cases. When you are going with respect to the right side, it is false. Then what will happen? This statement must become true and then this statement must become false. So is there any method where I can make my left side as a true and right side will become false? If your left side will become true and if your right side will become false, then what will happen? Then what will happen? Then we can say that means we can easily try to make the whole statement as a false. So for example, suppose if I will, with the help of little bit of experience, if I will put the value of A as a false and C as a false, then what will happen? This left side will become true, which implies, and let's consider this is also true, and then which implies, for example, the value of A as false and value of C as a false. Now what will happen? False implies false will become true. True implies this is true implies false and false will become false. True implies will become false. So the whole expression will turns out to be a false. So for example, if you will put this is your A, this is your B, this is your C. This is the truth table. If this is your truth table, if you will put the value of A as a false and if you will put the value of C as a false, even with respect to this also, and the negation of B is true. Negation of B is true. That means B is false. So even if you will put with respect to, suppose if you will take A as false, B as false, C as false, what you can see in this truth table. See, I'm not talking about all the rows. So do not get confused. I'm not talking about all the rows. I'm talking about only one specific row where A is false, B is false, C is false, and then the here answer you will be getting is false. So this expression is definitely not a tautology. So this is the main concept actually. This is the main concept. Where A is also false, B is also false, C is also false, then definitely we can say that here we are not getting anything, but here we are getting false. So that is why this expression will become not a tautology. Clear?
Yes, sir.
Okay. So in that way you have to understand. Okay. I hope that everybody can solve this. I think P implies R, Q implies R. In this, everything is a tautology. We have solved these two. Now, if you have any doubt related to any particular things, you can tell me. Okay, what about this? In this also, I think everything is a tautology. I mean, this and somewhere this is map. Okay, this one and this one, somehow questions are same. Last two. Okay, everything is a tautology here. I think most of the questions. Clear?
Yes,
Yeah,
sir.
the right side top question number C.
This one.
Yes, sir.
This one, right? Okay. So for example, your question is something like that. This it's saying that P or and then Q or R. This is one entity, and then and negation of Q, and this whole thing is implying, which is nothing but P or R. Now try to take the values. So for example, suppose if I will take the whole statement as a true, and then this statement will become false. So when the right side will become false, when your P is getting false here, and when R is getting false. So the value of P, you are getting this as false, and then the value of R, you are getting this as false. Now, if this must be true, that means this box must also be true, and then this box must also be true. That means if you are getting negation of Q as a true, then what should be the value of Q? Then the value of Q, you are getting this as false. So here, as you can see that, I mean, this negation of Q will also become a true. So the value of, we got the value of P as R false, R as false, and Q as false. So every value we got it. Now try to substitute it. Then what will happen? The value of P will become false, or value of Q is also false, or the value of R is also false. So false are false are false. Now what will happen? Then this whole thing will become what? This whole thing will become false. And now the false will see the and condition. Then what will happen? The whole left side will become false, and if the whole left side will become false, and if false implies anything, then what will happen? Then the whole statement will become what? The whole statement will become true. Understood? You do not have to do anything. You just have to, very polite way, you have to write down the values and you just have to come up and solve it. That's it. Now let's move ahead and let's try to find it out. See, if you will see very carefully with respect to the type 1, what I have done, I have used, which is nothing but your implication, right? And so when to use the type 1, because type 1 is having a limitation. So when to use the type 1, you have to use the type 1 whenever there is an implication, and then they are asking for a question, check whether this question is a tautology or not. So we have to use the type 1. So you have to be very specific. Now you must be thinking, sir, what will happen if there is some what will happen if there is a, instead of implication, if there is a double implication, something like that, or instead of implication, if there is an and condition, then we have to use which type? Instead of implication, if suppose if there is a or condition is there. So there are so many, the different types of things which will be related to that. What I'm trying to tell you is, you simply, whenever there is an implication, you have to use type 1. That's the main part. That's the main part. Whenever there is an implication, you have to use the type 1. That's the main part. Now, suppose if there is no implication, then what are the things that we have to do and we have to use it? So, for example, if there is no implication, suppose you can use the and condition, or what will happen? So, in with respect to that, we will be having the another type, and then that type is called as a type 2, and then type 2 is called as a logical equivalence. Logical equivalence. Logical equivalence. Logical equivalence. Logical equivalence is having a two different type of representation. This is your representation, or sometimes it is also used a double implication. So in some cases, in some questions, either you can say that the double implication is also used, and the three line is also used for logical equivalence. So yesterday I have taught you two different things, two or three different things. For example, when your A is logically equivalent to B, this A is logically equivalent to B when when A and B are having same behavior. When A and B are having, okay, when A and B are having the same behavior, right? Same behavior. Whenever you will have something like that, when A and B are having the same behavior, then you can go and you can try to use this concept, where A is logically equivalent to B, where A and B are having the same behavior. This is the first point you have to understand. A and B are having the same behavior. What is the meaning of it? That means A can be true and B can also be true. Suppose if A is a false, B is also false. Another way of saying that, suppose if your A is logically equivalent to, A double implication B is a tautology. A double implication B is a tautology. Then we can say that, this is a point number 2. So point number 1 is basically same as the point number 2. You have to remember this point. Point number 1 is always the same as point number 2. Point number A says that A is logically equivalent to B, where A and B are having the same behavior. What I'm trying to tell you here is basically what kind of type 2 questions you will get. In type 2, they will give you this expression and then they will say that check whether this one is a tautology or not. So instead of using just a single implication, they will try to give you double implication and then they will try to find it out to check whether this expression and this expression is a tautology. So this is related to your type 2. Suppose if they will give something like that, where the first expression and then double implication, second expression, they are saying that check whether it is a tautology or not, then how we will say? We will say that this is your expression A and this is your expression B. So suppose if expression A, double implication expression B is a tautology, they are asking, suppose if they are asking, another way of writing, if you can find it out, if they are logically equivalent, then either you can say like that or you can say like that. Now, what is the meaning of logically equivalent? Logically equivalent. Again, I'm repeating, please focus. In type 2, what kind of questions you can get? You will have one expression, double implication, you will have second expression. So here you will have expression A, double implication, you will have expression B. So expression A, double implication, expression B is a tautology. Suppose if they are asking some questions like this. Now, suppose if they are asking some question like this, then another way of understanding, we can say that, suppose if this expression is logically equivalent to this expression. Now, what is the meaning of logically equivalent? Logically equivalent means whenever they are having the same behavior. That means suppose if any cases, if this whole expression is a true, then this must also be true. Suppose if this whole expression is a false, then this statement will also be false. So this is another way of proving it. Or there is one more method, and that method is we have to solve A and we have to solve B and we have to make A look like B, or we have to make B looks like A. So how we can do that? We are having the different types of formulas and then we can go and we can try to use it. I know that whatever I'm teaching you are not getting it until unless we'll solve some kind of questions. So instead of solving those kind of questions, first we will try to understand some formula. So that formula will help you to make A looks like B, or you can make the B looks like A. That is the formula. Let's try to understand the type 2 today, and that is related to logical equivalence. So for example, here these all are the methods. First, suppose if I'm having A and A, then I can say that it is logically equivalent to A. Suppose if I'm writing A or A, then it is also logically equivalent to A. And then everybody knows about it, right? Second type of formula, suppose if I'm writing A and 2, and then I should be having some value, and I don't know what is A and true will looks like. Then what I'll say that, suppose if this is A and true. Now what I can say that, suppose if I don't know what is the value of this or what exactly the A and true will looks like. So what I'll say that I'll try to substitute the value of A. Suppose if I'll substitute the value of A as a true, then what I will get? I will get the answer as a true. So if you are substituting the A as a true, you are getting answer as a true. Suppose if you are substituting the A as a false, then what you will get? The answer you will be getting is basically false. So what I'm trying to tell you here, whatever the values of A you are substituting, you are getting the same value. So here A and true, my answer will become A. Now suppose if I'm writing A or false, then what is the value of this equation. For example, if I'm writing A or false, so the value of A can be either true or it can be false. For example, suppose if you'll put the value of A as a true, then true or false will become true. Suppose if you are putting the value of A as a false, then false or false, you are getting false. That means whatever the values of A I will put it, I will always be getting the same answer. So this is the second type of, you can try to understand, this is not related to type 1. Basically it is related to what? Basically it is related to your you can say that logical equivalence. So A and true, the answer we are getting as A, and A or false, you are getting answer as A. Now let's talk about the third one. Suppose if I will be writing A or true, and then what should be the answer? I don't know the values of anything here. Then
So true.
A or true is there, right? So everybody knows that OR loves true. So easily we can say that OR loves true here, right? So the whole answer will become true. Now if I will be writing A and false, then what will happen? And hates false, and everybody knows that this equation where and hates false. So I can easily try to say that the whole statement will become what? The whole statement will become false. So this is nothing but related to this. Now let's move. These all are the things which is very much important when you will have a very large expression A, and when you will have a very large expression B. So whenever you will have an expression A, whenever you will have an expression B, so you try to solve expression A, and then you will try to looks like B. Or whenever you will have an expression B, you will try to solve B, and you will try to make a looks like A. So in order to do that, we will require the different kinds of formulas here. Now let's move to the fourth one. Here I can say that A or B is logically equivalent to B or A, and A and B, and then this is also logically equivalent to B and A. See, this looks like very simple, right? A and B is logically equivalent to B and A, and A or B is logically equivalent to B or A. This looks like very simple, but when the large amount of things it comes in your practical point of view, then this is very important to solve. For example, suppose if you'll have a P or some expression, something like that, and then this is A and B implies R. Let's consider this is nothing but your one expression. Okay, let's consider this is nothing but your one expression. Now what will happen? This expression will something like this. Then this we can also, in another way, we can write A implies and then B implies R. This is your one box, and then you can write OR P. Now what we are very much handy, whenever we will have this expression, then we can easily try to write down this expression. Whenever we will have this expression, then we can write down this expression, right? This is we are very much handy. But my main point is, whenever you will have this expression, then we are not getting, sometimes it's not that easy to get clicks such that we can also write P or and then A and then B implies R. So do not think that this is just A or this is just a B. This A you can consider as a compound propositional statement. This B also you can consider as a compound propositional statement. Do not think that A is your simple propositional statement. Do not think that B is your simple propositional statement. You try to think like A as a compound propositional statement. Or in another way, you can say that your A will be looks like this, and then your B will be looks like this. So here, this is your A, and then this is your B. You'll try to consider like this. Now in A, you can put as many as variables you can put it. In B, you can put as many as variables you can put it. So that's how you can try to get it. Okay. So this is related to fourth point, where A and B, they are not basically the simple propositional statement, but basically they are the compound propositional statement. So you always try to understand related to this. So this is very, very important whenever you will try to understand. Okay, so that's the main point. So let's move to the another the relations. So suppose if we'll move to the fifth point, then here we will be having, which we can write as A or and then B or C, and then this is logically equivalent to A or B and then or C. And another way of writing A and then B and C, this is also logically equivalent to here A and B and then and C. right? So whenever you'll be having related to the fifth point, again you do not have to, am I audible? Right. So do not think like that A is a different simple propositional statement, B is a simple propositional statement. Try to think as A as a compound propositional statement, B is also compound propositional statement. These all are simple. Till now, I don't think we'll have any type of problem related to your first one, related to second, third, fourth, and fifth. Now, suppose if we'll move to the sixth one, here the sixth one is very, very important. So please pay attention. For example, if I will write A or and then B and C. See, this is called as a commutative law. Every law is having a different types of name. So do not think like that you'll have the different types of name or something like that. I don't want, see, I do not believe on this you have to remember each and every name. There are different types of name. For example, idempotent is there, okay, and then this is identity law, and then this is you can say that the true law, and this one you can say commutative law, this one is associative law, and this one is a distributive law. I'm not telling you to remember any name. I'm just trying to tell you based on the operator. You have to play based on the operator. I will say that even in examination, because if I will force you to remember the different types of name, 100% you're gonna forget it. And this type of law are used in a different places. In digital logic, Boolean algebra also you'll have this kind of law. In set theory also you'll have this same kind of law. And here also you'll have a same kind of law. So I'll say that you do not try to use, okay, do not try to use any different type of name. What I can say that you try to see the operator, and based on the operator you will take your decision. So here this is the fifth one. So how you can identify the fifth one? Your operators are same basically. So A or B or C, it's same as A or B or C. A and B and C is basically same as A and B and C. So your operators are same. So whenever your operators are same, you can switch the bracket. Whenever your operators are same, you can switch the bracket. So for example, here, as you can see that A or B or C, the bracket is here. That means with respect to this, the first you have to solve this particular bracket. Okay. And then in this, the first you have to solve this particular bracket. Again, I'm forcing on this particular point, this A, B, and C, they are not just a simple propositional statement. Basically, they are a compound propositional statement. So always try to remember this, which is nothing but A, B, and C. Okay, anyhow, let's move to the sixth point. The sixth point, how to identify the sixth point. In sixth point, your operators are different. Okay, try to understand that your operators are different. So here A or B and C, and then it is logically equivalent to, we can write, which is nothing but A or B, and here this is and then this you can write as a or C. So this is called a distributive law, and everybody knows about it. Now here I can write this as A and then this will become B or C, and again you can say that your operators are different. Here your operators are different, A or B and C. So these operators are different, A and B or C. Again your operators are different here. So this is taking an entry, and here it will become A and B, and then this will become OR, and then this will become A and C. So this is the most important one, distributive. Now I know that you may have studied this somewhere in 11, 12. I'm just doing a brush up related to this. My point is very simple. Many times we just remember the formula, and then that is moving from the left side to right side. What is the meaning of moving from left side to right side? Meaning of moving from left side to right side is basically I can write A or B and C. For example, suppose if you'll have something like that, A or B and C, then if this, you will have this is your left side, and then when you will go to the right side, what you will get? You will get A or B, and then here and it will become A or C, right? So this will take an entry here, A or B and C. You will get A or B and you will get A or C. So you will have the left side, and you will try to take an entry, and you will try to make the right side, A or B and A or C. My point is very clear. see, sometimes your left side has not been given, only the right side is given. So you have to identify your right side and you try to make that right side as a left side. Okay, so how you will try to identify, that's the main problem. So for example, let's consider this is A or, and this is also A or. So you will be having in the left one also you'll have a or, in the right side also you'll have a or. Try to have a string on this. Try to say that, try to consider a or. You know, try to consider like this. Try to plug one string on a or and try to plug one string on a or, and then plug it and then remove it like that. Then what you will get? You will get the left side, which is nothing but B and C. So sometimes it is very much important related to this type of things. Clear?
Yes, sir.
Right? Good. So this is a distributive law, and then this is very important. Now let's move to the next type of law, and then that is called as absorption. So for example, here if I will write A or and then A and B, and then this whole thing will become A, or another way of writing this is A and A or B, and this whole thing will become A, right? So this one and this one both are basically the law. What this one is trying to say, that this is saying that A or A and B, it is logically equivalent to A, and then A and A or B, and then it is logically equivalent to A. This one is also logically equivalent to A, this one is also logically equivalent to A. Let's try to find it out ki how we are getting, or how we can try to solve it, where A or A and B is logically equivalent to A, and this one A and A or B is logically equivalent to A. Let's try to go and let's try to find it out. So for example, suppose you'll try to understand like this, how to identify the absorption law, because absorption law is very much important. Whatever is written outside, that also has been written inside. Whatever has been written outside has also written inside, and your operators are different. For example, if your operator outside it is or, then inside you will have the and condition. So this is the main criteria to understand the absorption law. Whatever is written outside, it is also written inside, and then operators are different, and your operators are different, then it will become the absorption law. So let's try to discuss many things related to your absorption law. So for example, here I can say that this is A is here and then A is here. Whatever has been written outside, it has been written inside, and then your operators are different. See, it does not depends on B. That is why it is called as the absorption law, because A is absorbing everything. Whatever has been written outside, it is also written inside, and then your operators are different. So here A or A and, then what you will get? The answer you will be getting is basically what? The answer you will be getting is basically A. Now suppose what will happen? Why you are getting this answer? For example, suppose if I'll put the value of A as a true, so the A will become true, or A will become here true, and now as you can see that the or has seen the true, then the whole statement does not matter what you are writing. Then the whole statement will become what? The whole statement will become true. So that means if you'll put the value of A as a true, or true, and the whole statement will become true. Now suppose if you'll put the A as a false here, what you will get? False. A will become false, and then this is or, and then this will become false, and now as you can see that this and has seen the false, so the left side will become false, and here you will get false. So false are false, hence the whole statement will become what? Hence the whole statement will become false. So this is the main criteria in order to understand that. So how to have the absorption law? Whatever is written outside, it is written inside, and then you will get the values of A. Okay, that's how you can try to make the concept related to your absorption law. Whatever is written outside, it is written inside. Whatever is written outside, it is written inside. Now the next one, which is called as a De Morgan's law, and then how the De Morgan's law will be looks like.
Sir, can eighth be seen by the distribution also as well?
Which one? You can write as 8th, 7th as a, you can also try to find out with respect to distribution. See, suppose if you use the distribution, what you will get? A or A, and then again and you will get A or B. So what you can write? Again the same situations, A or A will become A, and then A, and then this will become A or B. Again the same situation, you will get this point. If you use the distribution, you will get this point. If you use distribution here, you will get this point. So you will be roaming like this. At the end, somewhere you have to come up with one value, right? Okay, let's move to the next one. Absorption law, De Morgan's law. De Morgan's law, this is negation outside, and suppose if we'll have this operator, when the De Morgan's law enters, it changes the operator. So here you will get negation of A, or will become and then this will become negation of B. And here this is negation A or B. When this negation enters, you will write negation of A. I have written the same thing. For example, here this is negation, and then this will become A and B. And suppose if this negation enters here, this will become negation of A or negation of B, right? So the first one, suppose if there is a negation A or B, and if the negation enters, negation of A or will become and then this will become negation. So do not think that this A is a simple propositional statement. No. These all are compound propositional statements. With respect to this also, for example, suppose if I want to show you the absorption law. For example, what is your absorption law? This is A or and then A and B, and then you are getting A. How to identify it? Whatever is outside, it is inside, and operators are different. For example, suppose if I will write something like that, let's consider that A implies B, and here A implies B, and then or, and then this is nothing but C implies D. Now, what is your answer? The answer you will be getting is A implies B only. Basically, this is the absorption law, right? So this, you try to understand this whole complex, you can immediately write as A implies B. So how to identify this? Identification is very important. This box you will try to consider as a capital A, you will get and. This box you will try to consider this as capital A. So again you will be having this capital A. And then you will get or. This whole box you will try to consider this as capital B. So here I am writing the capital B. So my answer will become what? A. Understood? So that's how we have to use it. Okay. Now let's go and let's try to understand. See, this is related to all the formulas which is related to and or type of conditions. Now we are moving to the implication. So in implication, there is one greatest formula that you people can try to understand. So let's talk about that greatest formula. And that greatest formula is, for example, see, whenever you will have A implies B, this is also logically equivalent to negation of A or B. This is a very greatest, the formula. And trust me, this formula is so powerful. Whenever you will try to, use this formula, in many cases, you can solve many questions. Trust me, you can solve many questions. Whenever you will try to use this formula, A implies B, which is logically equivalent to negation of A or B. But how this is true? First, you can try to use this with the help of truth table. And your truth table, this is your A, this is your B, this is A implies B, and everybody knows that this is true, true, this is true, false, this is false, true, and then this is false, false. So here you will get true, this is false, this is true, this is true, and then negation of A or B. What is your negation of A? This will become false, false, true, and true, right? मैं lecture में हूँ. Lecture mein hu. So the first one will become what? So here negation of A or B. So false or true will become true. False or false will become false. True or true will become true. And then true or false will become true. So as you can see that this will have the same behavior, same column. A implies B, true, false, true, true. And this is also true, false, true, true. So we can say that A implies B is logically equivalent to negation of A or B. That's the one point. That's the one thing. But I'm not trying to focus. I'm not trying to tell you that you have to use that, the truth table every time. I can say that this A implies B is logically equivalent to negation of A or B. This you are using at each and every day. Seriously. Every day you are using this. A implies B. For example, suppose you are writing the statement कि if you go late office, then boss may fire you. Boss may fire you. Right? Suppose if you are writing A implies B, something like that. If you go late to the office, then boss may fire you. Sometimes you are also writing another way. What we are writing? We are writing that don't go late to the office. Don't go late office or boss may fire you. Sometimes we are using in our normal language. For example, suppose at your home also, people used to say, your mom used to say, my mom used to say that if you wake up late in the morning, then I will not give you breakfast. Another way of saying, don't wake up late in the morning or I will not give breakfast. So I gave you explanation with respect to the truth table also, and I gave you the explanation with respect to the normal behavior. So this expression is very, very important. Do not try to forget it. So here you will have, for example, this A implies B is logically equivalent to negation of A or B. This is the first type of explanation. And the second type of explanation is A implies B is also logically equivalent to, we can write negation of B, that will implies negation of A. A implies B is same as writing negation of B, that will implies negation of B. These two are so powerful. These two are so powerful. With the help of this, we can solve many questions. And personally, I used to call in my class this as God's rule. God's rule. The second one is a contrapositive. I hope you remember that. I personally call this as the God's rule. I personally call this as God's rule, where A implies B same as negation of A or B, or another way of writing, A implies B is logically equivalent to negation of B, that will implies negation of A. These two rules are very much powerful. And whenever you don't understand anything, whenever if you don't understand anything, try to use these two rules. 100% it will help you. 101% it will help you to understand this. Anyhow, let's move ahead and let's try to solve more questions. So here the next one, suppose if I'm writing A implies B and A implies C, then this is logically equivalent to, it says that A implies, which is nothing but B and C. This is your rule. A implies B and A implies C. It is logically equivalent to A implies B and C. Now, how to solve this? Or see, as I was talking while teaching that this is a type 2. So let's consider this is your A, and then let's consider this is your B. Let's consider this is your expression A, and then this is your expression B. This was the thing I was talking about. Initially, I told you that left side you will have one expression and right side you will have one expression. Left side you will have one type of expression and right side also you will have a one type of expression. You will have a two different type of expression here. Left side you will have expression A, right side you will have expression B. So we have to check here. This is the logically equivalence. The type is there. So we have to use. Okay, we have to check. We have to find it out. Okay, we have to check whether this A and B. Okay, we have to check whether this A and B, how they are logically equivalent. That means we have to solve. We have to use some method. So let's go. Let's try to use the different types of method here. See how this is equivalent. I'll try to prove it. So for example, let's consider this. A implies B and this one will become A implies C. Now this will become negation of A or B is here, and this is negation of A or C, right? We can use the God's rule. God's rule, in the God's rule, the first one will become a negation. So A implies B can be written as negation of A or B, and A implies C can be written as negation of A or C. Then what will happen? Now here distributive law, you can try to append negation of A, try to make a string on this negation of A and try to pull it. What you will get? Then you will be getting which is nothing but B and C. Here you can write B and C. Now try to use the God's rule in a reverse manner. Negation of A or B and C. What you will get? You can say that it will implies A and it will implies B and C. So it says like that. That's how you can understand this. Clear, everyone? So this expression is clear. I have solved it. Now let's move to the next one, and that everyone please pay attention. So here if I'm writing A, that implies C, and here I will write B, that implies C, and then it is logically equivalent to. So for example, suppose if I'll write like this, A implies C and B implies C. So here I am writing A implies C, and then and it says B implies C. So A implies C, what I can write? I can write this as negation of A or C, and then and what is this? B implies C. B implies C can be written as negation of B or C. Now what we have to do? We have to use or C and then or C. Try to take outside or C. What you will get? You will get negation of A and negation of B. So if you take negation outside, what we can write? We can write negation outside, and then we can get A or B, right? A or B or C. Can I write like this? The negation of A or B or C. Now, what exactly is the negation of A or B or C? Can I write like A or B or this implies C? Can I say like that?
So,
Yes, sir.
Right? So the answer for this expression, you can get it. It says A or B, and then this whole thing is implying C. Now, one thing you have to make in order to understand this is, see, when the left side is the same, here you will have A and here you will have A. When your left side is the same, your operator is not changing. Your operator is not changing. But when the right side is the same, then the operator is changing. Why it is changing? Just because of De Morgan's law. It is changing. Getting my point?
yes, sir.
Now, if I will write, okay, I want you to solve this. Here, I have used two AND condition, but what will happen if I will use a OR condition? So A implies B or A implies C. What should be the answer that you can try to find it out? And then again, I will write A implies C, or then if I suppose if I'll say that B implies C. What should be the answer related to this? You tell me and you try to solve this. So the answer for this one, what you are getting? Left side is same, operator will not change. Right side is same, operator will change. I hope everybody got the same answer. Right? Yes. Now, as you can see that, suppose if I'll give you this question here, okay. Now, as you can see that this question is, they are not asking the type 1, they are asking the type 2. So if you solve it, what you are getting the answer related to this? Can you tell me? See, the first thing that you have to do is put the negation inside. Try to take the negation inside. Bro, I'll solve it. See, for example, here this is your question, and it says that negation of P, first it is a negation, and then it will have P or, and then this will become negation of P, and here it will become Q, and something like that. What you can do, try to take this negation inside. This will become negation of P, the OR will become AND, and this negation will come here. This is negation of P and Q. Now, if this negation will go inside, what you can get? You will get negation of P. This and will be there, but here this negation will go. It will become P and then OR, and here it will become negation of Q. Now, as you can see that this is negation of P. This is and then this will become P or negation of Q. Now take this, the operators are different. If the operators are different, we have to use the distributive law. Now this is negation of P and P, or this negation of P and negation of Q. Now negation of P and P. So one of them will become always false. So here you will get false or negation of P and negation of Q. So false or it is totally dependent on this. So negation of P and negation of Q. So, oh yes, the option D will become right answer. Clear?
Yes, sir.
So type 2 you have to solve like this. You have to use all the method, you have to use all everything, and then based on that you have to find it out. Based on that you have to tell me. I hope that this has been clear to everyone. Try to solve this also. And get it. Right? Done? Both the questions? Yes or no?
Yes.
Yes, sir.
What is the answer for the first one?
P.
PNT?
PNT. PNT.
Right, PNT. Second one. And for this, A?
P.
Did you solve this one? A or B?
Explain second answer.
Second one, na?
Yes, sir.
Second one or first one?
Sir, could you solve, please?
Sir, can you solve second one?
Okay.
Sir, can you solve first one, sir?
Okay, I'll solve both. See here, this is P or P and Q, right? One bracket, and then here one bracket is also there. Or this is P and Q and a negation of R. First, I will solve this bracket. Now, as you can see that whatever is outside, it is inside. So this whole expression will turns out to be P or, and then P and then Q and negation of R. Again, whatever is outside, it is inside. Operators are different. So again, this whole equation will become P. The same situation will also be happened here. As you can see that this whole expression will turns out to be a P, and now this T is outside. You can also write like this. This is T or commutative law. Now this you can write P and R and T. Now whatever is outside, it is inside, and then operators are different. So this whole equation will turns out to be T. So that is why you will get P and T. Clear, everyone?
Yes, sir.
Yes, sir.
Okay.
Yes,
Now
sir.
let's see the second one. Second one, what it says? It says here you will have P. This is and then negation of R or Q or negation of Q. So first we will try to solve this. Now, if you will try to solve this, what you are getting? One is positive, one is negative. So whenever there is a one is positive, one is negative, you will always get one is false. Why? As you can see that, see, this is P or negation of P. Either you can, suppose if you put the value of P as a true, P can have only two values. Either P can be true or P can be false. Suppose if you are putting P as a true, then true or false, answer you will be getting as false. Sorry. Answer you will be getting this as true. Am I right?
Yes,
Yes,
sir.
sir.
Now suppose if we'll put P as a false, then what will happen? Suppose if we'll put P as a false, then the first one will become false, second one will become true. So again you will get answer as a true. So if one is positive, one is negative, you will always get a true, because one of them will always become a true. Am I right?
Yes,
Yes, sir.
sir.
So here this whole expression Q or negation of Q, so this will become P and negation of R or true. Now what is this? What is the answer of this you will get?
True.
True.
True, because or loves true. So here P and true. What is the answer you will be getting with
P.
respect to this?
P.
P. So this whole expression will turns out to be what? P. This whole expression will turns out to be P. The same situation will also happen here, but here this R is positive and negation of R is negative. But instead of writing together, they have written differentially. But the operator is same. So you can use the associative law. You can write R or negation of R or true. So this thing will become true or true. Again, whole thing will become true and a negation of Q. So if you will use this, what you will get? You will get negation of Q. So the first one will become P, while the second one will become negation of Q. So P or negation of Q. So that is why you will get option B. Clear?
Yes, sir.
Did you get the idea how to solve this?
Yes, sir. Yes,
And
sir.
the same formula will also be valid in Boolean algebra. The same formula will also be valid into the set theory. So for example, suppose here I'll try to give you one matrix. This is, I personally call in my class, this as the God matrix. What is this God matrix? Whenever you will have the AND in Boolean algebra, you will have a dot. In set theory, it will have an intersection. And if there is a OR in Boolean algebra, in distal logic, you will have the OR. In set theory, you will have the union. And true in mathematical logic, here it will become 1. False in mathematical logic, it will become 0. In set theory, it will become universal set. And here it will become 5. So for example, I'll try to show you. Suppose if I have the absorption law, A or and then A and B, this is absorption law, I can easily write as A. Suppose if I want to make this theorem into set theory, I will write A union and then A intersection B. So suppose if this is A, suppose this is A, this is B, A intersection B, you will get this part, right? So A union A intersection B, what you will get? You will get A. Suppose if you will use this thing into Boolean algebra, A plus A dot B, and then again answer you will be getting as A. So that's how you people can try to use it. So you just have to learn one particular theorem. Either you can learn with respect to distal logic, or you learn with respect to here. This formula is valid for logic. Here this is for Boolean algebra, and this is for set theory. So you just have to remember one particular formula. If you know about logic, you can solve Boolean algebra. If you know about Boolean algebra, you can solve the set theory. So these all are interrelated with each other. So either if you'll remember one, you can remember all. Yesterday, what we have covered, we have covered type 1 and type 2. And today we will be going and we'll be starting with the type 3. And type 3 is related to the inference rule. Inference rule. See, basically, if you will ask me related to type 1 or type 2, I'll say that the more you practice, the more you will get that answer. That's it. This is the only difference related to your type 1 and type 2. Again, the whole logic is based on the concept of practicing. The more you will practice, the more you will get that answer. And it is very simple actually. There is no rocket science into this. Whatever the formula that we have is, discussed yesterday, again, in that also, everything is dependent on that. Okay, so let's start with that today's topic, and then that is called as the inference rule. What exactly is the inference rule? Let me try to understand, or let me try to give you an explanation with respect to this related to your inference rule. See, this is very simple concepts related to your inference rule. In order to understand the inference rule, the one thing that you have to understand is basically whatever the concept you are, remembering for type 1, just forget type 1. Because when you will be having the type 1, or when you will try to connect your type 1, then you will not have, you will not understand the inference rule. That's the main concept. So the first thing that you have to understand, you just have to, forget about type 1. We will use, see, at the end I will tell you whenever you will see a question, and then when to use the type 1 and when to use the type 3. See, for example, when I taught you type 1 and then you practiced 4 to 5 questions, and then you understood that, sir, type 1 is very easy, we can try to solve all the questions with the type 1, right? But when you will see the type 3, I mean, this is your inference rule, this is your type 3. Whenever you will see this type 3, then what will happen? Once you will understand about the type 3, then you will be having this concept ki, sir, type 3 is more easy as compared to type 1. But the type 1 is more advanced actually. Not advanced. Type 1 covers many things, but type 3 is having more limitations. That you can only understand once you will understand about the type 3. So let's go and let's try to understand related to type 3, which is nothing but your inference rule. So what exactly is the inference rule? First I will try to give you the definition of inference rule, and then I will explain you. So initially 15 to 20 minutes you will not have that idea. You will be thinking, "Arey sir, what exactly is the inference rule and how you are getting that inference rule?" And I know that you will have a large amount of problems related to this. What exactly is the inference rule and how we can try to solve the questions related to the inference rule. So I know that you will be having a problem. I know that you will be having the main things related to this. But anyhow, what I'm trying to tell you, just give me 15 to 20 minutes. Initially 15 to 20 minutes, you will not understand anything. But after 20 minutes, when you will try to connect all the dots, this, when you will be trying to connect all the dots, at the end you will get to know that, oh, this exactly is the inference rule. So let's try to understand. See, whenever you will see this sign, first of all, just forget about type 1. Whenever you will see this particular sign, I'm trying to first define the inference rule. And I know that you may have also studied the inference rule in your college, but you are just knowing about the formulas, modus ponens, modus tollens. But what is the history behind it? How you are getting modus ponens is valid. That I will try to explain you. So what exactly is the inference rule? Inference rule says that whenever you will see this particular sign, whenever you will have this particular sign, just try to understand this particular sign, okay? Whenever you will see this particular sign, then what you have to do? You have to see what has been written on the left side and what has been written on the right side. See, whenever you will see this sign, whatever has been written on the left side, that is called as a premises. And whatever has been written on the right side, that exactly is called as a conclusion. So there are two things basically. One is called as a premises, another one is called as a conclusion. Whatever has been written on the left side is called as a premises. Whatever is written on the right side is called as a conclusion. These two things you have to understand. These two things you have to understand. Whatever it has been written on the left side is called as a premises. Whatever has been written on the right side is called as a conclusion. Now, you may have a doubt. What exactly is a premises? Let's try to take the example. For example, if I will write A implies B or C. One example. So this one is called as a premises, while this one is called as a conclusion. So that's a very simple things related to inference. If I will say that A implies B or C, this is just a random I have written. Random example I have written. Whenever you will say that A implies B or C, then your left side is called as a premises, while the right side is basically called as a conclusion. Now, if I will be writing ki A and B and then it will implies, then this thing will called as a premises, while this one is called as a conclusion. So it's all about the left and right side. So what exactly is a premises? Premises is nothing. This is also a propositional statement. This is also a propositional statement. I just need 20 minutes. After 20 minutes, I will connect everything. Whatever has been written on the left side is also the propositional statement. Whatever has been written on the right side is also called as a propositional statement. So everything is a propositional statement basically. So as you can see that this over here, this is called as a propositional statement. and whatever has been written on this side, this is also called as a propositional statement. So everything is a propositional statement basically. My point is very clear. Premises is also propositional statement, conclusion is also propositional. Both are propositional statements. So it's all about left and right. Whatever the propositional statement has been written on the left side is called as a premises. Whatever the propositional statement which has been written on the right side is called as a conclusion. So that's it. It's all about the left and right. Whatever you are writing on the left side is called as a premises. Whatever you are writing on the right side is called as a conclusion. See, your propositional statement can be simple or it can be compound propositional statement. For example, here the left side is a simple propositional statement. Right side is a compound propositional statement. Left side is a simple propositional statement. Right side is a compound propositional statement. Or it can be mixture of anything. For example, it can also be very simple. This is also simple. This is also simple. Or for example, let's consider key. This can be compound also. This left side is also compound. Right side is also compound. So it's not just simple or compound or something like that. It's a very basic concept. Whatever you are writing on the left side is called as a premises, and that exactly is a propositional statement. And whatever you are writing on the right side, that is also the propositional statement. Right? What exactly is that? That is simple and compound. You have to understand like that. And it's all about the left and right side. It's everything is all about left and right side. Whatever you are writing on the left is called as a premises. Whatever you are writing on the right is called as a conclusion. So what exactly, sir? What exactly is the inference rule? Inference rule says that consider the premises as true. Okay, consider the premises as true. Consider the premises as true and check the conclusion and check the conclusion and check the conclusion and check the conclusion. So you have to consider your premises as true. What exactly is the premises? The left side is a premises, and you have to consider that as a true. So consider that left side as a true. When you will consider the left side as a true, you have to check the right side. What exactly is the right side? The right side is what? Consider the premises as true and check the conclusion. Now, conclusion may have two things. First, suppose if your conclusion is also true, then that whole expression will become valid. The whole expression will become valid, and then that comes under the inference rule. So you do not have to do anything. You have to consider the premises as true. When you are considering the premises as true, when you are taking your left side as a true, what you have to do? You have to check the right side. What can be the right side? Right side can be true or right side can be false. Suppose if your right side is coming as a true, then there is no point of having the false. Everything is become true. Everything will become true. So when everything will become true, the conclusion will become a true, and if the conclusion will become a true, then this will comes under what? This will comes under the inference rule, and then this is very simple actually. Then whole thing will become what? The whole thing will become valid, and then this will comes under the inference rule. What will happen if your conclusion will become false? So as soon as your conclusion will become false, then it is not valid. Then it does not comes under the inference rule. This is a very simple concept. This is one way of writing premises and conclusion. Another way of writing, you can also write like this. Here this is your premises, vertical way. This is your premises, and then therefore you can write which is nothing but your conclusion. So here you can have this conclusion. So you can write the horizontal way, premises, which implies the conclusion, or another way of writing here premises and then the conclusion. So either you can write like this or you can write like this. See, sometimes you may have a different types of premises. I know that you are thinking, sir, I'm not getting anything. And I told you, just give me 20 minutes. After 20 minutes, everything will become okay. Everything will become easy actually. Now, what you have to consider, the left side, it can be the multiple premises. For example, here you will have the premises number 1. I mean, you will have the one type of propositional statement. This is, you will have the another type of propositional statement. So the left side can have a multiple premises. So premises number 1, premises number 2, premises number 3. And let's consider there are n number of premises, and then that leads to what? And then that leads to, which is nothing but what? Which is nothing but one conclusion. So here you will have the multiple premises. Premises number 1, premises number 2, premises number 3. There are multiple premises, and then multiple premises leads to what? The multiple premises leads to the conclusion. Now, what is your main thought about it? Your thought is very simple. You have to consider the left side as a true. Now, consider this statement as a true. Whenever you are considering left side as a true, and what you have to do? You have to check the right side, right? So when you are taking your left side as a true, okay, when you are taking your left side as a true, that means I can say that this must also be true, 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 and then there will be an and condition between all. So this is one way of writing in a horizontal way, or you can also write in vertical way. Let's consider this is nothing but premises number 1, this is nothing but premises number 2, this is nothing but premises number 3, and then there are multiple premises, and that leads to what? That leads to conclusion. This is one way of writing, and then this is another way of writing. So till now I just told you two things. First one, the definition of inference rule. What is the definition of inference rule? It says that take the left side as a true and try to check the right side, what exactly it is coming. Right side may be true or right side may be false. So if you're taking your left side as a true, for example, P1, P2, P3, I mean this whole left side, okay, try to take this left side, this whole left side as a true, and then check the right side. I mean, try to see that what you are getting the right side is true or not. This is one way of writing. The left side, try to consider the left side as a true and try to check the right side is conclusion is coming as a true or not. So this is one way of writing. Or here, this is the definition. Consider the premises as true and check the conclusion is coming as a true or not. So you will have two options. For example, suppose if you are taking your conclusion, and if the conclusion is coming as a true, then it will become a valid, and then we can say that it comes under the inference rule. Conclusion, and then the conclusion, it implies true, and then true implies valid, and then 100% it will comes under the inference rule. 100% will comes under the inference rule. Otherwise, it does not comes under the inference rule. Sir, I have not understood anything. I know that. Initially, you will not get anything. But once I will try to cover many things, then you will try to understand many things related to that. For example, let's consider one premises here. This is one premises, and every time you have to consider your premises as a true. For example, suppose if I'm writing my mobile phone, here this is one premises which I'm, see, it's not just about the mathematics. You can create your own rule into the inference rule. Inference rule will give us powers so that we can generate our own rule. We can make our own rule, but we have to follow the certain things. And what are these certain things? We have to consider the premises as true. Consider the premises as true. So here this is my one premises. I am taking one premises. I am trying to generate one rule here. Okay, I am trying to generate one rule here in a simple way. So let's consider there is one premises, and it premises says that mobile phone, either it is in left pocket or right pocket. Okay, mobile phone, it is in left or right pocket. Left or right pocket. Okay, here this is one type of example. My mobile phone, it is into the left pocket or right pocket, and this statement is true. 100% this statement is true. There is no doubt into that. This is the first premises, and 100% it is true. It must be into the left pocket or it must be into the right pocket. I mean, there is a or condition is there. So either it is in left pocket or it is in right pocket. Now here I'm taking the another premises, and that premises is also true. It is not in left pocket. It is not in, okay, it is not in left pocket. It is not in left pocket. For example, let's take this example. It is not in left pocket, and this is also, this statement is also true. It is not into the left pocket. So what should be your conclusion? Just forget about the mathematics. Just tell me with in a simple manner. Suppose if mobile phone it is in left or right pocket, and the second premises which is also true, and it says that it is not into the left pocket. What should be your opinion on this? Then 100% it must be in right pocket. Then I can say that it must be in right pocket. It must be in right pocket. Is this true or false? What should be your opinion on this? We can definitely say that the statement will become true. Yes or no? It must be in a right pocket. Here I am having the first statement. Mobile phone, it is in left pocket or it is into the right pocket. This is the first statement, and which is true. Second statement, it is not into the left pocket. Then 100%, what should be your conclusion? Conclusion, it must be into the right pocket. Now, let's try to prove these things with the help of mathematically. So for example, here I'm writing my first statement. Okay, I'll try to convert into the logical expression. Logical expression says that mobile phone, it is into the left pocket or it is into the right pocket. This is your first expression. Now, second statement, it says that it is not into the left pocket. So this is your first premises, this is your second premises. And the conclusion, it is showing that it must be into the right pocket. So how we can try to write it down? This we can try to write it down. Here you will have the first premises, this is your second premises, and then it leads to what? It leads to the conclusion. So this is the way of writing, horizontal way of writing. What is your first premises? Your first premises will become L or R. This is your first premises. And this will become the first premises, and second premises will become, which is nothing but negation of L. And what it says the conclusion. The conclusion is basically R. So now let's try to implement the concept of inference rule here. And the concept of inference rule says that try to take the left side as a true. Try to take the left side as a true. Okay, try to take the left side as a true, and try to check the conclusion is coming as a true or not. We have to check the conclusion is coming as a true or not. So this thing we have to understand. We have to take the left side as a true. Okay, we have to take the left side as a true, and we have to check the right side is true or not. So how we can try to understand? See, let's try to take one truth table here. So I'm having this truth table. This will become L, this will become R, and then here you will get L or R, and this is, for example, let's consider this is negation of L, and then here you will get L or R. Now, with the help of truth table, I'll try to show you. We have a different method. I'll try to show you with the help of this. For example, this will become true, this will become true, this will become true, this will become false. Here it will become false, this will become true, and then this will become false, this will become false. Negation of L, what you are getting? This you will get false, this you will get false, and then this you will get true, and then this you will get true. Now L or R, what it will become? True or true? Here you will get true. True or false? You will get this as true. False or true? You will get this as true. False or false? You will get this as false. Now, according to this premises, what the premises says that first premises L or R, when it will become a true, it is becoming true here, it will become true here, it will become true here. And where is this negation of L? Negation of L is becoming true here. Now, according to the inference rule, it says that try to take the left side as a true. So I am trying to take this as also true, and I am trying to take this as also true, and I will try to check the conclusion. What is my conclusion? So if I am trying to take this one as a left as a true, here it will become true, it will become true, it will become true. When I'll try to take this as true, it will become true here, true here. But there is a AND condition, so I have to take this particular row, because this is my first premises, this is my second premises. Now check the conclusion. My conclusion is coming out as a true. So we can say that this will become your inference rule. So if I'm trying to take my left side as a true, when I'm trying to take my left side as a true, I have checked the conclusion. The conclusion is also coming as a true. So when this happens, then it comes under the inference rule. When it comes under the inference rule, then the whole expression will become a tautology. It will never become false. It will always become a true. If your R is becoming, okay, if your R is becoming false, if your conclusion is coming, okay, I want everyone to use the type 1 in this and tell me whether this one is tautology or not. Then it will be helpful. Then you can understand a better way. So any expression which satisfies the inference rule, any expression which satisfies the inference rule, it comes under any expression which satisfies the inference rule, then it will become valid. And how it will satisfy the inference rule? Your left side must be true. If you are taking your left side as a true, then you have to check the right side, and then the right side will also come as a true. When your right side will become as a true, then only it will become the inference.
Sir, yeah, it is a
But it is a
tautology.
tautology from first one.
It is a tautology from type 1. So that means
Yes.
if you check it is a tautology, why it is a tautology? Because it is satisfying the inference. See, it's a very simple. Here there is an implication. When the implication will become false? When the implication will become false? When you will take the left side as a true, but Here, if you take left side as a true, right side immediately is coming out as it. So it will never become a false. Then it will become a rule.
Sir, even if we take right side as false, we cannot make the left side as true completely.
See, we are not talking about in inference rule. We never talk about right side. We always talks about the left side. So you have to take everything as the left side. You have to
Sir,
take
in
everything.
tautology, we need to take from left side of true and just we need to take for right side false. Then we need to compare. Okay.
That is type 1.
Yes, sir.
Type 1, see, type 1 is basically to check something.
Yes,
Let
sir.
me be very clear. Type 1 is basically to check whether it's a tautology or not. Type 3, it will gives us power to create our own rule. Here I can create my own rule. I'll show you. So for example, what we have done, here we have taken L or R. Okay, one way of writing horizontal, left or right, and then and negation of L, and then this whole thing is implying R. This is one way of writing. Another way of writing, I can write L or R and then negation of L, and then therefore you are getting this as R, right? Or see, this L or R, do not think that this is left or right. This L is one type of compound propositional statement. R is also one type of compound propositional statement. So here, as you can see that this is positive, this is negative of that positive. So answer you are getting as R. Do not let me be very let me give you a point. Do not think that it's like a mathematics you're cancelling and here getting answer. No. Inference rule says that with the help of the first premises and with the help of second premises, you are concluding something, and that conclusion is R. I'm just trying to help you. One is positive, one is negative. I'm just trying to help you. One is positive and one is negative. So how I can create my own rule? For example, if I will write like this, A implies B or C implies D, then negation, if I will write A implies B, and then I can write my conclusion, which is nothing but C implies D. This is one way of writing. So here I have created my own rule. I can create that particular rule. Because if this is valid, then this will also become a valid. Or another way of writing, how I can write it here, this A implies B, or here I can also write like this, A implies B or C implies D. The whole thing will become and negation of A implies B. This is the first premises, this is the second premises. See, there is no order. You can consider this is also first premises, this is also second premises, because there is an and condition in between. So if there is, do not think like that. This is premises 1, premises 2, then there is an and condition in between.
Sorry, it will be the R condition. So
No, there would not be or condition. There will always be and condition between two premises. So what this conclusion will say that your conclusion will become what? Your conclusion will become C implies D. So this will become your conclusion. It's a very simple concept. This is your conclusion, C implies D. In a very simple manner, you can easily try to get it. This is your C implies D. So A implies B or C implies D and a negation of A implies B. This whole thing is concluding, which is nothing but C implies D. And that's how we can make our conclusion. Getting, not getting?
getting, sir, getting.
Getting,
This
sir.
is the first type of rule. We can create your own rule. See, what I told you, if you are writing this, for example, rectangle, and this is your oval, okay, and here you will have this or condition, and suppose if there is a negation, and in this, suppose if something like this, then what should be your conclusion? The conclusion will become this oval. Now, it's up to you. You want to fill 100 variables into this place, you can fill it. You want to fill 200 variables into this, fill it. For example, if I'll write A implies B or C, B or C. Here, if I will write C implies D and X. Now, here the negation will become, because this is your rectangle, this is also rectangle. So that means whatever you are writing here, you have to write here. So this is A implies, this is nothing but B or C. What should be your answer? The answer will become C implies D and X. C implies D and X. So this will become your answer. This will become your answer. C implies D and X in a simple manner. So one is positive, one is negative. Do not think, let me warn you, do not think that this is positive or negative. Do not think that this is positive or negative. This is your first premises and this is your second premises, and these two premises leads to one conclusion. This is the first premises and this is your second premises, and then it leads to the conclusion, and then you will have this conclusion, something like that. See, I know that you will have a doubt. Okay, let me try to explain you. Just now what we have understood, the first rule, if you will say that, sir, if there is a or B and if there is a negation of A, what should be our conclusion? The conclusion will become B. This is one way of writing, or you can also write like this. Suppose if you will have A or B and if there is a negation of B, then this is also A. So either you can consider like this or you can consider like that. So A or B negation of A, answer you will get B, or A or B negation of B, you will get answer is B. So either you will have like this or you will have like this. Getting, not getting? See, there is no things to repeat it here. See, this is very simple. A or B, A or B. For example, what you can write, the first expression you can also write like this. According to the commutative law, first one you can write B or A, and then this one will become negation of B, and what you are getting that answer? Getting that answer is A. So this is also same. This is, I mean, your rule, you can write like this or you can write like this or you can write like this.
Yes, sir.
Okay, let's take, this is one way of creating a rule. So you know, the one type of rule we have created. Let's try to take the another rule. See, here this is my first premises. My first premises says that if perfect matching exists, this is the real time example. If perfect matching exists, then number of vertices will become even. Then number of vertices will be even. Then number of vertices will be even. Will be even. This is my first premises. Now, second premises, I'll say that there is one graph where the perfect matching exists. Then what should be your conclusion? You tell me. What should be your conclusion? What should be your conclusion? You tell me, everyone.
Since will be even.
And then the conclusion will become what? Okay. The conclusion will become what? The conclusion will become the number of vertices will become even. Number of vertices will be
even.
Will be even. Now let's try to use the, you know, the logical expression of that. Logical expression with respect to the first one. Here you will say that P implies Q. This is the first logical expression. Where the perfect matching exists, the number of vertices will become even. P implies Q. What is the second logical expression? Second logical expression will become P, because P is for perfect matching. Because if you are taking this one, okay, if you are considering this one as a P and if you are considering this one as a Q, then what will happen? Here it will become P and here it will become Q. So P implies Q and P. Then what should be your conclusion? Conclusion is Q. This is one way of writing. Another way of writing, you can say that like this. P implies Q is there and P is there, and then the whole thing is implying Q. Now, according to the inference rule, I will try to consider the left side as a true. I will try to consider the left side as a true according to the inference rule. That means I have to take this statement is also true and I have to take this statement is also true. That means I have to check the conclusion. Now try to use the truth table here. So this will become P, this will become Q, and then this will become P implies Q. Now what will happen? This will become true, this will become true, this will become true. Now this will become true, this will become false, and then this will become false. This is false, this is true, and then here you will get true. This is false, and then this will become true. Now try to understand this. For example, according to the inference rule, P implies Q, I have to take this statement as a true. That means I have to take this as true, I have to take this as true, I have to take this as true. What should be the second premises? P. You have to take the second one also true, but second one is only true at this point. So what is the combination? I have to see the first row. That means if I will take this premises as a true, if I will take this premises as a true, the conclusion it is showing every time this is true. I hope that you are getting that why I am taking only the first row. I'm not taking any other thing, but I'm only taking the first row because the first row it's showing me the combination of first premises and second premises true value. I cannot take this because here the second premises will become false, so I will not take this. Here the second premises is coming as a false, so I will not take this concept. And here the first premises is showing me false. So I have to take those cases where the first premises and second premises both will become true. When both will become true, then I have to see the conclusion. My conclusion is coming out to be a true. So in that way, I can say that this will become it comes under the inference. Definitely it will come under the inference. Okay, I'll show you one beauty of God's rule. See, this is P implies Q, and then this is P. Therefore, this is Q. Use that God's rule. What you will get that God's rule? Negation of P or Q, and then this will P, and then therefore you will get Q. Can I write like this? One is positive, one is negative. Both are focusing on. I mean, see, whatever you are writing here, this must be the negation of that. But it is already a negation. It is already negation of P. So that means, can I write like this? Yes. Understood now? Because what is our method? This is your box and then this is oval. This must be negation of this and then you will get oval. For example, suppose if I will write negation of P here, then again it will become negation of P. Negation of P, you will get P and then you will get this. Understood? Not understood?
Yes, sir. Understood.
Everyone?
Yes, sir.
Right? Yes or no? Good. Now, everyone try to understand this point and what exactly it is trying to say that. It says that when your left turn left gets matching, when left one and left one gets matching, then you are getting the answer which is nothing but Q. And here you are getting answer which is nothing but what? Which is nothing but Q. So P implies Q and then left side you are having P. So left and left getting matching and then the answer you are getting is basically Q. So you can also try to have your own rule. For example, let's consider this is the box and then there is an implication and here you will be having this oval thing and now you will have this box and if you will take that conclusion, the conclusion will become what? The conclusion will become this oval. It's a very simple. Now it is a time to show you what kind of example is not comes under the inference rule. So here this is my first premises. This is the premises number 1. If I will write if perfect matching exists, then number of vertices will become even. Then number of vertices will be even. Number of vertices will be even. This is your first premises. Second premises, let's consider there is a graph. G is having even number of vertices. This is nothing but your second premises. The first premises I have written and then this is nothing but what? This is nothing but your second premises. So if perfect matching exists, then number of vertices will become even. This is your first premises. And second premises, it says that G is having even number of vertices. Now, can I write my conclusion that G contains perfect matching? What should be your opinion on this? G contains perfect matching. Then perfect
Sir,
matching.
it may or may not be.
It may or may not be. That's a very wonderful answer. That means even if I will consider this statement as a true, that if perfect matching exists, then number of vertices will become even. If I will consider this first statement as a true, and even if I will consider the second statement as a true, if I will consider my first premises as a true, if I will consider my second premises as a true, And if I will check my conclusion, the conclusion must be true. But here it is showing sometimes it is true, sometimes it is false. So when it is showing sometimes it is true, sometimes it is false, that means I will not consider this under the inference rule. I will not consider this under the inference. I will not consider this under the inference rule. It's a very simple concept. Let me show you with the help of a truth table. What this truth table shows that if perfect matching exists, so I'll try to take this as P implies Q, and this will become your first premises, this will become your second premises. Second premises is Q. Now the conclusion they are asking for P. So this is one way of writing. Another way of writing, this is one way of writing, okay, and another way of writing is basically P implies Q, and here you will have Q, then that whole conclusion it says related to P. Now let's try to have the truth table. The truth table says that this is P, this is Q, this is P implies Q. Here let's consider this is true, this is true, this is true, this is false, this is false, this is true, this is false, this is false. True implies true will become true, true implies false will become false, false implies true will become true, this is true. Where is your premises? First premises, P implies Q, and where it is getting true? It is getting true here, it is getting true here, it is getting true here. Where is your second premises? Q. Q is getting true here and Q is getting true here. That means if I will take a combination, now focus everyone. What it says, if perfect matching exists, the number of vertices will become even. If I will consider this as true, if I will consider this as true, my conclusion is P. That means sometimes it is showing maybe, sometimes it is showing may not. And that's the beauty of this truth table. It shows may and it shows that may not. Okay, sometimes it may be true, sometimes it may not be true. That is why this does not comes under the inference rule. Try to use. Okay, now as we can see that there are different types of rules we have seen. First type of rule is P implies Q, and then left side P, and then therefore, okay, therefore you are getting answer as a Q. This is one type of rule. Second type of rule, P implies Q, and if there is a negation of Q, and then therefore negation of P. Third type of rule, here if I will say that P implies Q and then Q implies R, so that you will get a conclusion. The conclusion it says that P implies R. Okay, then it says that P implies R. So P implies Q, Q implies R, and then the conclusion we are getting is P implies R. Now, and then the rule we have seen that this is P or Q and negation of P, and then therefore you will get Q. Another type of rule, suppose if there is a P and then this will become P or Q, and if there is a P and Q and then therefore this is P. Another rule, P or Q, negation of Q or R, and then therefore you will be getting which is nothing but P or R. So these all are the different types of rules we are having. Now let's try to understand one by one each one. Here this is one way of writing, horizontal way, vertical way, horizontal way you can also write it like this. And what it says here this is nothing but P implies Q and P, and therefore the whole thing is implying what? Q. And second one, P implies Q and negation of Q, and then this whole thing is implying negation of P. This is P implies Q and Q implies R, and then the whole thing is implying P implies R. See, let's try to understand. I don't think you need an explanation with respect to the first one. Let's try to understand the second one. Second one, I'll try to explain like this. P implies Q. What is the contrapositive of P implies Q? negation of Q, that implies negation of P. This is a contrapositive of the first one. P implies Q. This is nothing but your P. P implies Q. What is the contrapositive of this? Contrapositive is negation of Q will implies P. And what is the second premises? Second premises will become negation of Q, and therefore you will get negation of P. So basically that is the same thing. And third one is a transitive rule. I don't think you need any explanation in order to understand the third rule. P implies Q, Q implies R, and that's how you're getting P implies R. Let's talk about this one. This I have already explained you, and I don't think you need any explanation related to this. P or Q and negation of P. Therefore, the whole thing is implying Q. Second one here, P implies P or Q. Now, see what the inference rule says. See, this one is important. Try to understand this. What the inference rule says? Inference rule says that take the left side as a true and try to check the right side is coming as a true or not. Now, if I will take this as true, then what will happen? Then P will become true. When the P will become true and true will see or, what will happen? What will happen?
All will be
Whole
true.
thing will become true. Everything will become true. Yes or no?
So,
Yes, sir. Yes, sir.
So this is one type of rule. Now, so I can write like this. Here it says that P implies P or Q. Now here this I can say that P and Q, and then this whole thing is implying P. Now try to take the left side as a true. When you will take the left side as a true, P and Q, that means if you will take left side as a Q, P and Q, what you are getting? You are getting both as a true. Left side will only become a true when both will become a true. That means at the same time P is also true and at the same time Q is also true. When P is also true, then what will happen? This will become true. Definitely this will become true.
But we can also use Q instead of P, right?
Ah, yes, you
Right
can
side.
use the Q instead of P. That's also good thing. And here one is positive, one is negative, you will get P or R. So we are having the different name to this. If you want, you can use the name. First one is modus ponens. Here, modus tollens. Here, hypothetical syllogism. Disjunctive syllogism. Here, addition. This is simplification. And this last one is resolution. So when you are comfortable into this, I mean, if you know all these rules, you can easily try to solve any type of questions which is related to your inference rule. And this exactly is the inference rule. It is nothing. You just have to consider the left side as a true and check the right side is coming as a true or not. So once you will solve this, you can easily get it, everything, all the answers related to this. You just have to remember these two things. I mean, if you remember this slide very clearly, you can understand, you can solve any questions. And trust me, whatever the questions which is based on the basics of logic, everyone can easily try to solve that. Everyone can easily try to solve that.
So
Okay, let's try to solve some question. So for example, suppose if we'll have some conditions like this, P implies Q and negation of Q or R, and let's consider, suppose if they are saying that, try to check whether this is valid or not. See, sometimes they will ask in the question in a horizontal way, or they can also ask the questions in vertical way. P and P implies Q and a negation of Q or R, and then this whole thing is implying R. So let's try to use the first one. First one says that first premises is P, which is given. Second premises is P implies Q. Now left side is matching. You will get Q. And then how you're getting? You're getting as a modus ponens. Now the third one, which is given, you will get negation of Q or R. So one is positive, one is negative, you will get R. And then this one is given. So again, you have to use the, either you can use disjunctive syllogism or modus ponens, no problem. You will get R. Easy. First, solve question number 8 and tell me it is valid or not. Question number 8.
Valid, sir.
Valid, sir. R, sir.
Yes, valid.
Valid? Okay.
Yes,
Solve
sir,
question
valid.
number 6.
Question number, sir?
6. Right? Okay. See, always how to solve this type of questions? You have to see the questions and you have to based on the conclusion you have to behave. See, for example, suppose if this question will come, then how I will solve? I have to see the conclusion. See, whenever you want to solve any type of questions, always try to see the conclusion. What is the conclusion? That the conclusion is basically W. But where is W? W, it has been given on the third premises. This is the first, second, third. See, it is not necessary this is the third premises. You can interchange. This can also be the first, this can also be the second. Because there is a AND condition in between all. So if there is an AND condition in between all, you can use at any point of time. My point is very simple. My conclusion is W. So where it has been given? It has been given here. That means T implies W. So if I want to make W as a free, I need T. So if I can get a T, then T and T left side matches, and then I will get the right side, W will be free. But where is T? T is given here, but it is not given in the form of T, but it has been given in the form of negation of T. I can use a contrapositive, I can get R implies tree. That means, where is T? I need T. That means if you need T, then T has been given in the left side or right side. T has been given in the right side. That means you need R. But where is R? R has been given here, R or S. So if you can make R as a free, then you can apply R here, you can get T, you can apply T here, you can get W. So let's try to find it out. So here first I will take negation of S and try to use the second one, R or S. One is positive, one is negative, you will get R. Try to use the contrapositive of this, R implies T, left matches, you will get right T. And then you will try to use T, T implies W, left matches, you will get implication as a W. Understood now? You don't need to remember any questions. You don't need to remember any type of answers. I mean, you don't need to remember any type of formula or something like that. Try to solve question number 9. P to Q, Q to R. What it will signify? P to R. Right? But here is negation of R. That means you can take contrapositive. Negation of R will implies negation of P. Negation of R you will take, and then answer you will be getting is negation of P. We can say that it is also valid. Question number 7.
Explain the seven.
So it is totally based on a practice. The more you will do the practice, the more you will get that answer. Solve question number 4. Okay, I think you need to give more explanation on this. Let me tell you one important point here. You can use P 2 times. For example, if P and P if you will use, you will get R implies S. And here you will get, what is the contrapositive of the first one? Contrapositive of the first one, you will get P implies R. P implies R, R implies S. These two you can write P implies S. You can use P one more time. And then therefore you will get S. Do not think that P will vanish. No, P will not be vanished.
Sir, we can use any number of times in that.
You can use any number of times, and then the reason behind it is basically something like that. For example, suppose if I will write like this, A and A, what should be your answer? You will get A.
A.
A and A and A, what should be your answer? You will get A. For example, if I will write A and B, either I can write A or A and A, or I can write A and A, or I can write A and A, because already know that there is a AND condition in between. So even if you will use these two condition, what you will get? You will get B. So you can use A as many as times A. So not a problem, because there is an AND condition. So A and A is A, A and A and A is A. So that is why here, if you, even if it is 1 times P, you can use it 2 times, 3 times. No, not a problem. Do not think that this P will vanish. Let me tell you very simple thing. This is not a mathematics. Ki 5 plus 2 will become 7, so 5 is vanished. No, it's like there are 3 things, and these 3 things are implying something, and that implication is S. Logical equivalence is a different. In logical equivalence, you can do like that. Logical equivalence is something different. Here, logical equivalence says that left side is equals to right side. Here, the left side is not equal to the right side. Your left side is implying. So I need to give a clarification on this, because many times the students are having a problem. For example, if I will write ki A implies B, it is logically equivalent to negation of A or B. So this is your left side, and left side is equals to right side. Here, if I will write A and A implies B, and then this whole thing is implying B. So what it says that this premises, this left side is implying something, and that something is called as a B. So implication is a different thing, while equivalence is a different thing. Equivalence means whenever you have A implies B, in place of A implies B, you can write negation of A or B. So you can delete it. For example, suppose if you will have x, it is equals to 5, and if I will write 2x plus 3, so in place of x I can write 5, so 2, 5 and then plus 3. This is mathematics, because x is equals to 5, so in place of x you can write 5. That is valid. But here this saying that this whole thing is implying B, so it is implying, it is not equivalent. Implying is a different thing, equivalence is a different thing. There is a difference into that. Clear? Today I will tell you where to use the type 1 and where to use the type 3. So by seeing the questions, you can easily try to get it. Okay. Now, if you will try to see the first question, in the first question, there is no need to use the inference rule, and there is no need to use this concept. What we can say, we don't need to use the concept of type 1, we don't need to use the concept of type 3 in the first one. You know why? Because this question is related to, as you can see that this question, the first question is related to this. If the right side is same, then the operator will change. This question is belongs to logical equivalence. Am I right?
Yes.
Right? Okay, let me tell you a very beautiful thing. Whenever there is a double implication B, so A double implication B, it is logically equivalent to, that means A can imply B, and at the same time B can also imply A. So A can imply B, and at the same time B can also imply A. This is the beauty of double implication. This is the beauty of logical equivalence. Whenever there is a double implication B, that means A can imply B and B can imply A. Now we know that this part is logically equivalent to this particular part. So that means the A can imply B and B can also imply A. So both can, A can also imply B and B can also imply A. Understood the first point?
Yes, sir.
Okay, what about second one? Second one is valid or not? You can use the Watt's rule, negation of P or Q, negation of R of S, and then P or R. If you combine these two resolution, one is positive, one is negative, what you will get? You will get P or S.
Q.
Next one, P or Q. One is positive, one is negative. Again, that means you will get Q or S. So the second one is valid. Easy? Yes or no?
Yes, sir.
Okay. What about this?
Sir, can you repeat the first two ones, sir?
First one, this one.
Yes, sir.
This one is basically, if you remember that in the type 2 logical equivalence, when I was teaching you the concept, there I taught you this box is equivalent to this box. Whenever one box is equivalent to another box, that means equivalent means double implication. So whenever there is a double implication, that means if A is logically equivalent to B, or if A is double implication to B, that means A can also imply to B and B can also imply to A. So we know that this is our box A and box B. So A and B both are same. So A can imply B and B can imply A. So here A is implying B.
So if it is in the box, we need to consider it as a double connection.
Yes. Okay.
Yes, sir,
Everyone?
third one is valid.
Okay, fine. Any problem with respect to this slide? Please let me know. This is a gate question, and we have already solved this gate question with the type 1, but I want you to use the type 3. Now, see the first question. See, whenever there is an implication, try to use the God's rule, the God will help you. That is a very simple concept. So what you can use, you can write negation of P or Q. Second, R is implying S, that means negation of R or S. And that means here you will get P or R.
Sir, yes, sir,
So
valid. Sir.
one is this one is positive, one is negative, you will get P or S. Here this is negation of P or Q. One is positive, one is negative. What you will get Q or S. Now, if you use the God's rule here, you will get S or Q. So that is why the first one is valid. Right?
Yes, sir.
Okay. What about S? See the option S. By seeing the option S, can we solve this?
Yes, sir.
I don't
We
want to
can-
use
Yes,
any
sir.
formula. By
R,
see
R,
here,
P, P, Q.
for example, P implies R, P. Left to left match, you will get R.
R.
So R will be free here, right? And then this is P, and therefore you will get R. If you'll apply R here, one is positive, one is negative, you will get Q. So that is why we can write this as valid. So within 3 seconds, you can solve the question. If you have the practice of inference rule, within 3 seconds you can solve the question. So that is why the first one, this one is valid, this one is also valid. What about the Q? What about Q?
R, sir, as a conclusion.
Yes, but what they are expecting. For example, the first premises, as you can see that what they have written, they have written is negation of P and Q. Now you tell me, can I write negation of P and Q as different? I can write negation of P here and I can write Q here. So when we are writing vertically, can we say that there is a AND condition in between?
Yes, sir.
Right? So I can also write individual. Now here we will have this Q, and then that will implies, which is nothing but P implies R. Now use the Q here. So if you will apply modus ponens, what you will get P implies R. But here this is not P, this is negation of P. So try to use a contrapositive negation of R, that will implies negation of P. If I am using negation of P here, then what will happen? Negation of R, can we write like this? No, this is invalid. Why it is invalid? Because I told you, matching the left side you will get the right side, but matching the right side you will not get the left side. Understood?
Sir, in Q, we can take that one as premises and Q one as a conclusion, sir, in negation of P and Q. So,
In negation of P or Q, you can take this as one premises, you can, because there is already and a condition in between.
yes, sir. Within the brackets also, we need to consider as a different thing.
Or you can use a simplification rule. Negation of P and Q, it can imply negation of P one time. negation of P and Q, it can also imply Q. So which is also same thing. Clear?
Yes, sir.
Sir, how negation R implies negation P cancel?
I'm not cancelling. I'm just trying to say that negation of P and Q, you can take two different premises. See, for example, okay, try to understand in that manner. So, for example, if you will have A, if you will have B, and then, for example, A is implying C. So, either you can write like this is one way of writing, or you can also write like A and B, and then here A is implying C. So this way of writing is also same. This way of writing is also same. So this way of writing is also same. This way of writing is also same. Both are basically same. There is no difference into that, because when I was teaching you, then what you have see, for example, this is the vertical way. If you write horizontal way, what you will get? You will get A and B and then A implies C. So automatically this will become A and B, because there is an AND condition between every premises, right? Got it?
Yes, sir.
So here we can use that and try to use this rule R. You will not get the same problem that
Getting
you
negation.
face. Yes, the same problem you are getting. The question number 5, the same here. So this is also invalid. You will not get R. You will get more than that. So that is why the real answer you will get this one and then this one. Clear, everyone? Here you will get. Okay, now you try to see the first question and second question. Everyone try to see the first question and second question. Now in the first question, just scan it and tell me whether you will use a type 1 or you will use a type 3. Scan the first question. For example, in place of you, if I will be there, so what they have written P implies Q, and here they have written P, so therefore I will write Q, and then you will get R. That means at the end I'm getting Q and R. But this one is something different, right? So immediately I'll switch to type 1. So first I'll do the scanning, and I will get to know that okay, I cannot use the inference rule. Then I'll switch to type 1. So now you can use the type 1 in the first one. Did you understand when to use the type 1, when to use the type 1 or type 3? Clear?
Yes, sir.
Yes, sir.
Yes.
Second question, just do the scanning and tell me whether you will be using the type 1 or what you will be using. For example, see, I'll tell you a very simple concept. In inference rule, you just scan it and try to see that the adjustment you're getting it or not. So immediately if you're getting that adjustment, then I'll go. For example, suppose if you require more than 10 seconds to solve the questions based on inference rule, then you have to use the type 1. For example, first I'll see that okay, this is P implies Q and P. So if I will match P and P, okay, I'll write like this. P implies Q and P, then therefore I will get Q, and then there is a and R. So I'm getting Q and R. But here they are expecting something different. I'll switch to type 1. Then I will use the type 1. Now let's see the second question here. Okay, second question, something they have written. For example, let's go to option C. So here I have written P or Q or R, and then this is negation of Q. So one is positive, one is negative. I will get P or R within 10 seconds. I will get. So I will write this is true. I will use the inference rule. Now let's see the second one here. So in the second one, I am not able to adjust. But if I will try, I will get it. So instead of spending time with respect to type 3, I will use the type 1. Understood?
Yes, sir.
Clear, everyone?
Yes, sir.
Good. Try to solve this, what you are getting. Yes, you have to use the inference rule. For example, negation of P or Q and R, and then R implies S. Transitivity, if you use, you will get P or Q, that will imply S or T. From simplification, take negation of U. Negation of U from simplification, negation of U, that will implies negation of T. Negation of U, negation of, you will get negation of T. And right, you will get negation of T. And negation of S also I can borrow. So I can get negation of S and I can get negation of T. Use the contrapositive. Negation
Sir,
of
is
S or T,
getting
that will implies negation of
notation of
P or
P
Q.
to Q, sir.
Huh?
It's getting notation of P to Q.
P to Q. You will get P and Q. P and negation of Q. You will get this. Did you understand till now?
Yes, sir.
Not understood.
Yeah, understood. Sir.
Yes,
P
sir,
and
it's clear.
Understood.
Please explain.
P and, so it implies P and negation of Q. That means if you will take left side negation of S and negation of T here, left match, you will get P and negation of Q. And from simplification, you can take P outside. So it will become valid. It is valid. If you're not getting anything, please tell me. I'm here to help you. Don't worry about it. The question, the premises, what they have written is negation of P or Q, and then that will implies R, and that implies R. Second, R, that will implies S or T. If you will combine these two, A to B, B to C, what you will get? You will get negation of P or Q, and then that will implies S or T. If you take a contrapositive of this, you will get this negation S or T, that will implies negation of P or Q. This will become negation of S and negation of T, that will implies P and negation of Q. Till here, any problem? No problem, right?
No problem.
Okay. Now here we are having negation of S. Can I write this two as a two different thing?
Yes, sir.
Now here this will become negation of U, that will implies negation of T. Now if you will combine these two, negation of U, what you will get? You will get negation of T. That means at one place you are having negation of S, at the second place you will have negation of T. Can I say that there is an AND condition in between?
Yes, sir.
So that means if I will take here, then negation of S and negation of T. Here we are already getting. So modus ponens, I will get P and negation of Q. Simplification, I can write P here.
Okay, sir.
Now it is clear to everyone. Divyansh has shared one file, and in that, what the question is like this: F1 and F2, it implies F1 and F2, it implies F3. F1 and F2, it implies F3. Okay. F1 and F2, it implies F3. And F1 and F2, it also implies negation of F3. So the question is saying that this is also tautology and this is also tautology. That means it cannot be false at any point of time. And this one will also cannot be false at any point of time. That means what will happen? That means we have to take the cases basically in this they are asking. So for example, suppose if I will put the values of F3 as a true, right? Case 1, if I will put the values of F3 as a 2, so that means F1 and F2, it implies true here, and F1 and F2, it implies false here. But we know that everything is true. That means this is also true, and then that means this is also true. Now my point is, if this right side is false, then 100% this must be a false.
False.
If the right side is true, then because if you're taking this as false, you have to take this as false. That means if this is false, it will have three cases to get false. This true, false, false, true, and false and false. That means if, for example, here, even if I will take all the cases of this, there would not be any problem. Still, it will become a true. Because it does not matter on the values of, for this, it does not matter on the values of f1 and f2. Even if your right side is true, it does not matter on f1 and f2. So this is your case number 1. Case number 2, for example, you will take f3 as a false. So the first one, f1 and f2, it implies false here, and f1 and f2, it implies true. So basically it turns out to be the same condition. I mean, case 1 and case 2 both will become only one case. For example, f1 and f2, the whole summary, sometimes it is true, and f1 and f2, sometimes it is false. So even if it is implying to true, even if it is implying to false. See, with respect to this case, it does not matter on the values of f1 and f2. It will always be true. It will always be true. So hence we have to focus on this particular case. f1 and f2, it is false. That means both cannot be true at any point of time. Rest, it can have all the cases. So if you will see what you can write, f1, both f1 and f2 are tautology. No, it is not necessary. And f1 and f2 is not satisfiable. So f1 and f2, yes, it is not satisfiable. So option B is right.
Sir, can't it be C, like f1, f2 are not tautology?
Neither f1, see, neither f1 nor f2 are tautology. What is the meaning of it? That means f1 cannot be true, neither f2 can be true. But here in my cases, I'm getting f1 as a true. Here in this cases, I'm getting f2 as a true. So that is why the option C is not right. Okay. Any problem in this question? Okay. First, try to scan the first and tell me what you are getting that answer. Okay. Scan the first one and tell me you have to use the type 1 or you have to use the type 3.
So type 1.
Tell me immediately.
Type 1.
Type 1. Good. Option B?
So type 3.
Type 3.
Type 3. Immediately. And that is valid or invalid?
So that is valid.
Valid.
By seeing it, you can answer that question, right?
Yes, sir.
Yes, sir.
Okay. C, option C, try to solve. I think rest of this question, we don't have to find out.
Option C
I mean,
is
we don't have
valid,
to-
sir.
For rest of this question, we don't have to use the type 1 or type 3 because they have already given you have to use the type 3. There is no
Option C valid.
option C is valid or invalid.
Valid, sir.
Valid, sir.
Valid, sir.
Option D. Okay. Solve all. Tell me answer for all. Did you solve this question or you're solving
Yes.
right now?
Sir, we have solved it.
Okay. So immediately give me the answer first.
Sir,
For
Sir, G, sir. Sir, G, sir.
D.
G for goat.
G for good. I think this we have already discussed in the previous question.
So this is valid.
Yeah, it is valid. This one is P, that implies Q, that also implies R. This is P or S. This is T, that will implies Q, and here you will have S, right? Now, what will happen? For example, no. there is
Notation of
some
S, sir.
mistake. Now, if you will combine these two, what you will get? You will get P. Now take the first one, and P that will implies Q, that will implies R. What you will get? You will get Q that will implies R. So P implies Q, Q implies R. If you will combine this, you will get T implies R. Take contrapositive negation of R, that will implies negation.
Sir, F.
F. Okay, I'll tell you. Focus you will get immediately. Take P from here. Simplification. P and P. If you will use, you will get R and Q.
Yes.
From R and Q, you will take simplification R, R match, you will get S or T. Negation of
sir.
S, you will get T. So it is valid.
Sir, but there is Q.
Sir, in the
Sorry?
upside P and Q, how many
Q
we need to
there.
consider, sir? In
So
a option, P and Q.
in P and
Yes.
Q, you can take P outside.
No,
Simplification.
sir. When we compare from for P and Q and P implies R and Q, can you solve it, sir, once?
Sir, getting Q or T.
Yes, sir.
Okay. I'll solve it. But did you understand G? So shall I remove it? This one?
Yes, sir, you can remove, sir.
Okay, I'll write stepwise, so you will get it. For example, here the P and Q, I'm writing just all these things. So this is P and Q, which is given. So from this you can write P, and then this is simplification. Second premises is P that implies R and Q. So modus ponens, you will get R and Q. From this you can take R outside. Simplification. Next premises, R implies S or T. Modus ponens, you will get S or T. Negation of S is there, and then you will get T. So it is valid. Clear?
Yes, sir. Yes, sir.
Okay. C, I think we have already discussed, right? This you will get. If you don't understand anything, use God's rule. Negation of P or Q. This is negation of Q. One positive, one negative, you will get negation of P. And here you will have negation of R. And then there is a AND condition. So you can write negation of P and negation of R. Take negation outside, you will get P or R. Clear?
Yes, sir.
Sorry, sir.
E.
Yes, sir.
Take P and P. What you will get? Q implies R will be free. This is use God's rule here. You will get negation of Q or R. Here also use God's rule. What you will get? You will get negation. You will get positive Q or negation of P. One positive, one negative. You will get R or negation P. You can use P 2 times. You can use P. You will get R. Did I tell you that we can use P 2 times, 3 times?
Yes,
Yes,
sir, you
sir.
told.
So for E, you can get it. Understood? All this get question. Get questions are always easy, but because once you will have the habit of solving my questions, definitely the get questions will become easy. Get 2012 solve. Are you able to see?
Yes,
Yes,
sir.
sir.
Okay, solve. Okay. See, if you'll see this question, first question, if it rains, try to convert it into logical expression. If it rains, and do not use your brain while writing, while understanding this. For example, let me tell you, if you will read this statement and if you try to evaluate by yourself, trust me, you will forget everything. If it rains, then the cricket match will not be played. And then the cricket match was played, and then you'll think, okay, there was no rain. Second, read the second. If it rains, then the cricket match will not be played. It did not rain, so the cricket match was played. If you will read like this, if you will come up with your own evaluation, 100% both statement will become true. And here comes the beauty of mathematics. If it rains, cricket match will not be played. Negation of P. The cricket match was played. Okay, try to take the contrapositive. That means P, that will implies negation of R, P and P, and therefore conclusion. So there was no rain. So this will become valid, and then it will become very easily we can try to solve it. Second question. If it rains, first premises, if it rains, the cricket match will not be played. Fine. It did not rain. That means negation of R. Okay. Try to take contrapositive. P implies negation of R, and then therefore P. Now, as you can see that right side, matching right side does not imply the left side. So that is why the second one will become invalid. Understood? If you have remember, I have explained, sometimes may not.
Yes, sir.
Understood, not understood? Tell me fast.
Understood.
Understood, sir.
So that's the beauty of mathematics, bro. It will help you to solve all the questions. Just a second, and I am giving you all the new questions. Able to solve it? Able to see it, everyone?
Yes, sir.
Good. So this is one logical question. Try to convert this logic into variables and then solve. This you can solve immediately. This you can solve immediately. This is something that I have increased the level. So solve it and then we'll discuss about it. Let's close this topic today.
Sir, are these three different question or same question?
No, this is different. This is today I have given this question.
Sir, the para question is different from the above two, right?
There are three questions. This is first, second, and third. Okay. See, for the first one, if we are writing P double implication Q, this we can write as a negation of P implies Q, and Q that will implies negation of P, right? So here we have a two entities. So we can take one which we require by using simplification. So if you will use this, we have to use P. I mean, if you use the contrapositive negation of R, that will implies negation of Q. This is negation of R, we will get negation of Q. So negation of Q, either you can use this or you can use this, no problem, right? Suppose if I will be using this, by simplification, I will take only left part and take contrapositive negation of Q, that will implies P. From there, we can take negation of Q and hence we will get P. Easy?
Yes, sir.
Okay. Let's try to solve this. Take P from here, match it, you will get Q, match it, QQ. This R or S will be free. Simplification, you can take R, one positive, one negative. You will get negation of T or U. Simplification, you can take T and then you will get U. Valid?
Yes, sir.
Understood, or shall I write the whole thing?
Understood.
Everyone, please reply. If the band could not play rock music, so if that means negation of M, music, or refreshments were not delivered, then so if the band could not play rock music or the refreshments were not delivered on time, right? If then the New Year's party would have been cancelled. Then party cancelled and Alicia would be angry, right? This will become one statement. If the party were cancelled, so first one, negation of M or negation of D, this implies C or A. If the party were cancelled, implies then the refunds would have not made. Then the refunds would have to be made. Refunds. No refunds were made. So negation of refunds. Then what we have to, then the play music, we have to come up with M. Right? Is this the question?
Yes, sir.
sir.
Okay. So if you will take
Contrapositive. Second one,
contrapositive,
contrapositive.
negation of R implies negation of C. Negation of R, you will get negation of C. Take the contrapositive here. What you will get? You will get negation
Negation of
C or A.
A.
Am I right?
Yes, sir. Yes, sir.
So,
TR8 23.
C and A neighbors,
This
but
is AND, right? This is AND. And A. So if you take negation of C, take contrapositive for the first statement, what you will get? You will get negation. You will get C and A, and then that will implies negation of M or negation of D. See, we are getting negation of C. Can we write negation of C or negation of A by using addition rule? Why I'm writing this? Because I need here. So if you write negation of C or negation of A, this will implies M and negation of D. So I will require this. I was getting negation of C, but here I will require negation of C or negation of A. So by using the addition rule, I can write or negation of A. Am I right?
Yes, sir.
Sir, by using the true or false, so in that way you have been taken the addition.
No, you can use the addition rule here, na? Because see, they are telling ki in the left side this will be negation of C or negation of A. Here we are getting negation of C. If you are getting negation of C and we want this, so we can use the addition rule, negation of C or negation of A. So you can use it here, negation of C or negation of A. Left matches, you will get M and negation of D. And what will be my next step?
Simplification.
Simplification, I will require M. Clear, everyone?
Yes.
Okay. So this, I hope that everyone is comfortable in type 3 inference rule.